Hi students, welcome to our YouTube channel Knowledge Academy. The main aim of this lecture is to discuss about the electrical machines formulas in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever we upload a new video, the direct notifications comes through. While if any of you must have no lectures, then please comment in the comment section. We will definitely include all those information in the upcoming lectures. So why to waste more time? So let's get started. So now in the magnetic circuit, so you can see basically this is called as a magnetic circuit. Here there will be iron core, and here we are going to wound a primary coil, and here we are going to wound a secondary coil. So we are going to call this as a primary coil and this is a secondary coil. And now I am going to send a current of I1 in the primary coil. The primary coil has a turns, the number of turns of N1, and the secondary coil is going to have the number of turns N2. So because whenever I send a current I1 in the primary coil, as the current is passing through this coil, it is going to produce a flux. So this flux is going to pass through this core because the core has a huge amount of permeability. So flux prefers to pass through the magnetic core rather than the air. So therefore all the flux is going to link through this core. So it is going to pass through this core in this manner. So it is going to pass in this manner to make a closed loop. So you can see clearly here from this circuit diagram. So here N1 is called as the primary turns, or we can say the turns of the primary coil. N2 is called as secondary turns, or the number of turns of the secondary coil. And I1 is called as the current flowing in the primary winding. And L is called as the mean length of the core. Mean length of the core means is the total length. This total circumference of this core is called as the mean length of the core. So now I am going to convert this magnetic circuit into an equivalent electric circuit. So I am going to convert this magnetic circuit into equivalent electric circuit. So here flux will be like current. Here flux will be like equivalent to current, and the resistance and the reluctance of the core is equal to like resistance, which is equal to R. And here the voltage is nothing but it is the MMF, which is N1 into I1 is called as the MMF. So it is going to produce the flux in the core, and the core is going to have small amount of reluctance. So you can see clearly N1 I1 is called as the MMF, which is going to produce the flux in the core, and this flux is going to pass through the core. So core definitely is going to have small amount of reluctance. So that is represented by the symbol R. So these are the things that you always have to remember. So we have converted the magnetic circuit into an equivalent electric circuit. So B is equal to mu into H. So B is equal to mu into H, and flux is equal to magnetic flux density into area of the core, and mu is equal to mu naught into mu r. These are the very basic formulas. So B is equal to mu into H, and we can say B is equal to flux per area, or flux is equal to magnetic flux density into area, and mu is equal to mu naught into mu r. So now I am going to apply the Ampere's loop in this magnetic circuit. The closed line integral of H bar dot dl bar is equal to current enclosed. So you can see clearly that if you take the overall rectangular plane of, then you can see the magnetic field intensity is constant at each and every point in the magnetic core. So H into L, and both are always in the same direction. So therefore the dot product is equal to, because theta is equal to 0, so cos 0 is equal to 1. So H into L is equal to the number of times the current is going to enclose. It is nothing but N1 into I1. So if you take a loop which is covering all the sides of the core, we can say it is like a paper. It's like a paper. Then you can see clearly that this current is going to enclose. That plane with N1 into I1. So therefore HL is equal to N1 into I1. So I have already told you B is equal to mu into H. So H is equal to B by mu. So B by mu into L is equal to N1 I1. As I have already told you, B is equal to flux per area. So flux per area means L is equal to N1 I1. So if I take flux here, I am going to get here simply like this, N1 into I1 by, so say flux is equal to N1 I1 AMU by L. So if you take here L downward, so we are going to get like this. So phi is equal to N1 I1 A mu by L. If you take A mu downward, we are going to get N1 I1 by L by mu A. L by mu A is called as the reluctance. R is equal to L by mu A, where L is called as the mean length of the core, A is the permeability of the core, and A is the area of the cross section of this core. So R is equal to L by mu A. As you can see clearly the permeability of a core is very high, so therefore its reluctance is always less when compared to air. So this is the formula. So as I have already told you, N1 I1 is equal to flux into reluctance. By applying the electric circuit formula, N1 I1 is equal to flux into reluctance, or flux is equal to N1 I1 by R. So if you want to know what is the overall flux linkage, because each turn is going to produce a flux phi, then there are N1 turns, so therefore overall flux linkage is equal to N1 into phi is equal to L into I1, because the overall flux linkage is always directly proportional to the current I1. So if you remove the proportionality constant, you are going to get the inductance L. So overall flux linkage is equal to N1 into phi is equal to L into I1. So if you want L, so L is equal to simply N1 square by R, because if you substitute phi N1 I1 by R, I1 cancels, so we are going to get N1 square by R. So this is called as the L is equal to N1 square by R. This is the, you can say, inductance of the coil 1. So this is called as the inductance of the coil 1, primary coil, N1 square by R. Basically what I am trying to say is Amperian loop. If you want to consider Amperian loop, just consider a rectangular plane within this cross section area. Just take a rectangular plane, or you can say simply take a paper with this, from this mean core, just take a paper. So you can see that the current is going to get inside this plane with N1 into I1 times. It is called as the enclosed current. That is what I am trying to tell you. Take within this mean core length. So this is a, within this mean core length, assume that there is a plane of paper. So this current is going to enclose this plane of paper N1 into I1 times. So now we will discuss about another concept which is called as the Lenz law concept. So Lenz law concept. The true meaning of Lenz law concept. See, when Lenz law is included, what we have to see, listen carefully, there is a transformer core. There is a transformer core with the primary coil of N1 turns and the secondary coil of N2 turns. So for this primary coil, I am going to give a supply voltage which is V of T. So this is a plus minus. So current is going to go through out the positive terminal. So let me assume this is the I1 turn. So the current is going to flow in this manner. So you can see clearly direction of the current is going to make a closed loop in this manner. So like this it is going to pass. So now if you keep your right hand thumb, in this direction, so if you keep your right hand fingers, if you curl your fingers in the direction of the current, so you can see clearly your thumb is going to indicate the direction of the flux. So this is 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 the direction of the flux. So basically the Lenz law says that the current is going to induce in the secondary coil in such direction, the flux produced by this, it is going to oppose the original flux. So listen carefully, the current induced in the secondary coil, it is going to produce a flux which is going to act opposite to the original flux. So you can see clearly, as direction of the original flux is in the downward direction, and the flux produced by the secondary coil should be opposite, means it should be upward direction. So if you keep the fingers in the direction of this current direction, so you can see clearly the flux is producing upward. So this is the direction of the action direction of the current. So if you see clearly, if you draw the diagram in this manner, so you are going to get the current in this direction. So you can see clearly, suppose if you keep a load here, the current is going to flow from this terminal to this terminal. So this is said to be positive terminal and this is said to be negative terminal. So same thing I have written here. So now the Lenz law is already included. So you can see clearly the Lenz law formula is already applied, because the current induced in the secondary coil will flow in such a way so that the flux produced by the secondary coil will always oppose the primary flux, original flux produced. So E2 is equal to I2 into RL is equal to N2 into d phi by dt. So this is the actual formula we have to use whenever the length law is included. So E2 is equal to I2 into RL is equal to N2 into d5 by dt. So this is the formula that you should use whenever the length law is included. So now we will see what happens if length law is not included. Now we will see what happens if length law is not included. Same thing, same magnetic core, the primary coil and secondary coil. So now I am going to give a supply voltage of V of t for this primary coil. This is a positive and this is negative. So if I am going to send the current in this direction, so you can see clearly current is going to flow in this direction in this primary coil of N1 turns. So whenever the current is going to flow in this direction, keep your right hand thumb, keep your right hand fingers in the curl, or curl the right hand fingers in this direction, and the thumb is going to indicate direction of the flux. So this is the direction of the flux. So now you can see clearly with the current direction, whatever the current direction produced here, whatever the current direction produced, if you pull your fingers in the direction of the current, you can see clearly the flux produced by this coil is in the same direction of the flux. So we can say that the Lenz law is not included. As I have already told you, the Lenz law included means the current produced in the secondary coil it should be in such direction. So therefore, the flux produced by the secondary coil should always oppose the primary flux produced. But you can see it is not opposing, it is in the same direction. It means that the Lenz law is not included. So if you take the current in this direction, the current is going to make a closed loop in this direction. So you can see as the current is flowing from here to here, so this is positive, this is negative, so plus minus. So E2 is equal to, I into RL is equal to, now we have to include negative because the Lenz law is not included. So minus N2 into d5 by dt. If the Lenz law is included, just take it here positive. If the Lenz law is not included, just take here negative. So this is the concept that you always have to understand till you die in these electrical machines. So this is the formula that you always have to remember whenever you are dealing with the electrical machines basic course. Then let me tell you a small concept of these dot polarities. So dot polarities, how to choose a dot polarity? Suppose if you keep a dot here, and if you send the current in this dot, then the direction produced by this flux. Suppose if you keep dot here, and if you are going to send the current inside the dot, and because of that, if you try to find the direction of the flux, and similarly, if you keep another dot anywhere, and if you just have to pass the current in the dot, and still the direction of the flux produced in this coil should be in the same direction of the flux produced by the original coil, then we can say these are said to be same dot terminals. If your dot is positive, your dot is positive. If dot is negative, plus dot is negative. So listen carefully. Dots means very simple. For the dots, particular dot, just send the current to the dot. So try to find the direction of the flux produced by that coil and make a circle. So if in the under coil you want to know where is the dot is there, just assume somewhere dot is present and inject the current. And if you try to find what is the flux direction, that flux direction should be in the same direction of the original flux. Then we can say that simply it is not going to oppose that. So it should be supporting that flux. So that is called the positive terminal, or we can say dot terminal. Both dots will be always positive and both dots will be always negative. So now here, let me take, suppose I am going to cut the core. Suppose I am going to remove some part of the core section. Let me assume the length of this core section is equal to L2. So L2 is the core section where I have removed the core. Means it is a air is present here. So now this is a coil. So in this coil, the primary coil, I am going to send a current of I1. So the primary coil has a number of turns N1. So now, as you can see clearly, the flux is going to pass through two mediums. One is the core and the other is the air. So I have already told you, as the flux is flowing in these two mediums in a series manner. So we can see both these things are connected in the series fashion because the flux is same in the magnetic core and also in the air. So therefore, I am going to assume that just two things, just the reluctance of the core and the reluctance of the air gap. So this is RC means the reluctance of the core and RG means the reluctance of the air gap. These two are connected in series and flux is flowing through them in a series manner. So flux is flowing in this series manner. So what is the net MMF? MMF is equal to number of turns into current I1. So N1 into I1. So this is the equivalent electric circuit for this magnetic circuit. So this is said to be equivalent electric circuit for this magnetic circuit. So then what is the reluctance of the core is equal to the mean length of the core. So mean length of the core, let me assume this overall is called as a mean length of the core, which is LC by mu into AC, where mu is called as the permeability of this core and AC is called as the cross section area of this core. Similarly, RG is equal to reluctance of the air gap is equal to the mean length here now just L2 by here mu is equal to mu naught into mu r, as mu r is equal to 1 for air, so mu is equal to mu naught into AC is a, see you can see the cross section of the core and the cross section of the air for the same amount of size is very same, so therefore L2 by mu naught into AC. So you can see clearly that mu is very larger than mu naught, so therefore this value is lesser when compared to this value, so therefore RC is always lesser when compared to RG, so therefore RG is very high when compared to RC, means the reluctance of the air gap is very high when compared to reluctance of the core. That is the reason the flux preferred to pass through the magnetic core rather than the air gap. So now I want to find what is the overall equivalent reluctance, as the both are condenser is the net reluctance is the summation of the individual. So R equivalent is equal to RC plus RG. So now R equivalent is equal to RC. What is the value of RC? The reluctance of the core LC by mu into AC plus RG, the reluctance of the air gap, which is L2 by mu naught into AC. So do the addition, you are going to get the overall equivalent reluctance. So let me give you some important point, which is I have already told you the mutual inductance between the 2 coils is equal to N1 N2 by R. So here just remember one small formula. The mutual inductance is inversely proportional to the area of the core. Mutual inductance is inversely depends on the area where the coil windings are kept. So this is the important formula that you always have to remember. So mutual inductance is inversely proportional to its area. So mutual inductance is inversely proportional to area. So mutual inductance inversely depends on the area where the coil windings are kept. So listen carefully. The mutual inductance is inversely proportional to the area where the coil windings are kept. So mutual inductance is inversely proportional to the area of the core where the coil windings are kept. So mutual inductance is inversely proportional to the area of the core where the windings are placed. So this is a very important formula that you have to always remember. The mutual inductance is inversely proportional to the area of the core where the coils are kept. Mutual inductance is inversely proportional to the area of the core where the coil windings are kept. So mutual inductance is inversely proportional to the area of the core where the coil windings are kept. So let me give you a small important point. E is equal to 4.44 N1F5. So therefore E is nothing but which is the induced EMF in the primary coil, which is equal to 4.44 N1F5. So this is a very important formula. This is the RMS value of the induced voltage in the primary coil. If you want secondary coil, just replace N1 by N2. So therefore E is equal to 4.44 N1F5. So E is equal to 4.44 N1 into F into where flux is equal to N1 I1 by R. N1 I1 by R. So 4.44 N1 F into N1 I1 where R is equal to L1 by mu A. L1 by mu A. So therefore, if the simplification we are going to get 4.44 N1 square F I1 A mu by L1. So for a given core, for a given fixed core, 4.44 into F into I1 mu by L1 is a constant value. So therefore N1 square into A. So therefore this is E is directly proportional to N1 square into area of the cross section where the windings are kept. So therefore E is directly proportional to N1 square into A. E is directly proportional to N1 square into A. So therefore E is equal to 4.44 N1 F5. Phi is equal to N1 I1 by R. R is equal to L1 by mu A. So this N square into A. This is everything is a constant. So therefore N1 square into A. So E is directly proportional to N1 square into A. So this is a formula that you always have to remember. Suppose in the question this may be always constant. Frequency is constant, I1 is a constant, mu is a constant, and E1 is constant. So only these are the variables, N1 square into A. So is directly proportional to N1 square into A. See, for perfect magnetic material, means the magnetic permeability is equal to infinity. So if magnetic permeability is infinity, then what is going to happen for the reluctance of the core? I have already told you R is equal to L by mu A. As mu is equal to infinity, the reluctance will be 0. So therefore, the reluctance of the core of a perfect magnetic material is always equal to 0. I have already told you the inductance of the primary coil is equal to L1 is equal to N1 square by R. R is equal to L by mu A. So definitely the inductance is going to depend upon the permeability of the core. So if you change the magnetic core, then the permeability also changes. So therefore the inductance of the coil is also going to get changed. So the inductance of the coil is going to depend upon the permeability of the core. So this is the big thing that you always have to remember. So this is a two-winding transformer. So now let me see carefully here. Here L1 is called as the inductance of the primary coil, and L2 is called as the inductance of the self-inductance of the secondary coil. L1 is called as the self-inductance of the primary coil, L2 is called as the self-inductance of the secondary coil, and then N is the mutual inductance between the primary coil and the secondary coil. So now this two-winding transformer, we can draw equivalent circuit which is in this fashion, which is L1 minus M, L2 minus M, and this is M. So the remaining everything is same. So this follows the equivalent circuit from this circuit. So L1 minus M, L2 minus M, and this is M. So L1 minus M, L2 minus M, and this is M. So this is follows the equivalent circuit of this circuit. This is follows the equivalent circuit for this circuit. So for this two-winding transformer, we can replace L1 minus M, L2 minus M, and M. So this is follows the equivalent circuit for this circuit. So let me take another circuit. So you can see clearly there is a primary and these are the two secondaries. So we can say oral P windings are present. So this is a primary winding and there are two secondary coils. So now, see, I am going to apply voltage. So these are the dot terminals are already we have given. This is a dot, this is a dot, and this is a dot. So now I am going to supply a voltage of V1. If dot is positive, means here also positive, here also positive. If the supply voltage is V1, the induced voltage here is V2 and V3. If dot is positive, the remaining is negative. So let me assume this coil has a number of turns of N1, this coil has a number of turns of N2, and this coil has a number of turns of N3. So the current, let me assume I1 is a current which is flowing inside this dotted terminal. See, based on the transformer always, the transformer, whenever the current is going inside the dot in one coil, then the current is going to leave the dot from the other coil. This is the thing that you always have to remember. The transformer, if the current is flowing in dot in one terminal, then in the other coil, the current is going to leave the dot. So this is the primary, it is going to inside. Because of this flux production only, these coils are going to get the current. So therefore, it is going to leave the dot and is also going to leave the dot. This is I2 current and this is I2 current. So I1 bar is entering, I2 bar is leaving, and I2 bar is leaving because of this flux production, because of the flux produced in the primary coil, remember the current is going to induce in the secondary and the two secondaries. So I2 is leaving and I3 is leaving the dot. So now we have to always understand the NMF balance is always going to apply. NMF balance, which is N1 I1 bar is equal to N2 I2 bar plus N3 I3 bar, because this coil is going to produce the MMF, these are going to absorb the MMF. So because of this only, here we are going to get the MMF. So therefore overall production is equal to this production. So therefore N1 I1 bar is equal to N2 I2 bar plus N3 I3 bar. This is called as the MMF balance equation. This is producing, this one consuming. So the overall production is equal to overall consumption. So N1 I1 bar is equal to N2 I2 bar plus N3 I3 bar. So now, as I have already told you, if the number of turns increases, the voltage is also increases. So V1 is directly proportional to N1, V2 is directly proportional to N2, and V3 is directly proportional to N3. So replace N1 by V1 bar, V2 by N2 by V2 bar, N3 by V3 bar. So we are going to get the complex power equation. This is called as a balance power balance. Always you have to go for the complex power balance. The overall complex power supplied is equal to overall complex power absorbed by the loads. Overall complex power delivered is nothing but V1 I1 bar, I1 V1 bar I1 bar conjugate is equal to V2 bar I2 bar conjugate plus V3 bar I3 bar conjugate, because this is called as a complex power balance equation. The complex power produced is equal to complex power absorbed. So this is going to produce the complex power. The remaining two things are going to absorb the complex power. So complex power is equal to V bar I bar V1 V bar I bar conjugate. This is conjugate only for the current. So V1 bar I1 bar conjugate is equal to V2 bar I2 bar conjugate plus V3 bar I3 bar conjugate. This is called as a power balance equation or complex power balance equation. You can go for MMF balance or you can go for the complex power balance. Complex power balance, you are going to get the same result. Suppose there is an auto transformer. Suppose there is an auto transformer. You can see clearly this is a primary and this is suppose I am going to make an auto transformer from a 2-wire transformer. So you can see this is in this fashion. So this is plus minus plus minus. So we can say clearly this is called as the additive polarity, because both are plus minus means overall voltage is increased. So this is called as the additive polarity. Suppose the voltage of this coil is V1 with the turns of N1 and overall voltage across the terminal is V2 with the overall turns of N2. So then I am going to keep a resistor of R1 here. Then what is the equal resistance across this terminal is equal to N1 by N2 is equal to V1 by V2. So N1 by N2 is equal to V1 by V2. So R equivalent is equal to simple just transform here. So your transfer from here to here is take this by this. So N1 by N2 whole square into R1. So N1 by N2 is nothing but V1 by V2. So simply R equivalent is equal to N1 by N2 whole square into and R equivalent is equal to N1 by N2 whole square into R1. So N1 by N2 is equal to V1 by V2. So this is the simple formula that you always have to remember. If they are asking what is the equal resistance of R1 with respect to primary coil, with respect to here, it is nothing but R equivalent is equal to N1 by N2 whole square into R1. N1 by N2 is nothing but V1 by V2, because these two are in the series I2 polarity. So when a single phase transformer is reconfigured as auto transformer, then KVA rating of the auto transformer is equal to KVA rating of the two-winding transformer by 1 minus K, where K is called as the low voltage of the auto transformer by high voltage of the auto transformer. This is an important formula that you always have to remember. So when a single phase transformer is reconfigured as an auto transformer, then KVA rating of the auto transformer is equal to KVA rating of the two-winding transformer by 1 minus K, where K is called as the ratio of the low voltage of the auto transformer by high voltage of the auto transformer. So whenever a single phase transformer is reconfigured as an auto transformer, then the KVA rating of the auto transformer is equal to KVA rating of the two-winding transformer by 1 minus K, where K is the low voltage of the auto transformer by high voltage of the auto transformer. It's a very important formula. So if you apply this formula directly, you are going to get the KVA rating of the auto transformer. So you can say that whenever a single phase transformer is reconfigured as auto transformer, then KVA rating of the auto transformer is equal to KVA rating of the two-winding transformer by 1 minus K, where K is the ratio of the low voltage of the auto transformer by high voltage of the auto transformer. When we keep full load as single phase transformer and it is reconfigured as auto transformer, then its KVA rating is increased. And if we load that auto transformer with that new rating, then in both machines losses are still same. So power loss is equal to iron loss plus copper loss at full load, and X is equal to 1 in both the cases. Yes, see, whenever we keep full load at single phase transformer, whenever you keep a full load at single phase transformer, the rated currents are going to get down. So whenever the rated currents are going to get down, you can say full load copper loss and the total loss is equal to iron loss plus full load copper loss. Iron loss is independent of the load. So therefore, you can say the total loss in the single phase transformer is equal to iron loss plus full load copper loss. And now we are going to change into auto transformer. See, whenever you are going to rechange into auto transformer, definitely the auto transformer rated KVA, the KVA rating of the auto transformer is always higher when compared to KVA rating of the single phase transformer. So because of that, if this new rating KVA, if you apply this new rated KVA to this auto transformer, it is also going to draw the rated current. So these rated currents are same as the these rated currents are same as the rated currents of a single phase transformer. So same copper loss is going to get present. So overall loss is also same. This iron loss plus copper loss full load. As both are operating at rated load, so H is equal to 1 in both the cases. So whenever we keep a full load at single phase transformer, and if it is reconfigured as auto transformer, then its KVA rating is increased, and if you load that auto transformer with that new rating, then in both the machines losses are still same. It is the losses is equal to iron loss plus copper loss at full load, and X is equal to 1 in both the cases. So when we keep full load at single phase transformer, and if it is reconfigured as auto transformer, then its KVA rating is increased, and if we load that auto transformer with that new rated KVA, then in the both machines loss are still same. This power loss is equal to iron loss plus copper loss at full load, and X is equal to 1 in both the cases because both are operating in the rated condition. So this is the thing that you always have to remember. So whenever you are transferring a single phase transformer into auto transformer, its KVA rating is increased. So if you keep the KVA rating for a particular transformer, the full load KVA rating of the transformer, then we can say the currents drawn are the rated currents. So the overall loss is equal to iron loss plus copper loss full load. Now if you are going to change into auto transformer, the rating capacity increase. So with this new rating capacity, if you keep a load with this new rating capacity, it is also going to draw the same amount of currents in the primary and secondary coils. So same amount of copper loss full load, iron loss is independent of load. So overall loss is same in both the single phase and also in this auto transformer. So power loss is equal to iron loss plus copper loss at full load, and both are going to operate at the rated loads. So we can say X is equal to 1. This point that you always have to remember. See, voltage rating and current rating are directly proportional to dimension square. So voltage rating and current ratings are directly proportional to dimension square. Whereas the KVA rating is directly proportional to area of the core and area of the core and the area of the window. Area of the core and the area of the window. It means that dimension square is nothing but dimension to the power of 4. Whereas iron loss is nothing but is also called as a core loss. It is directly proportional to dimension cube. Whereas the core loss current and also the magnetizing current and no load current and the inductance and the magnetizing reactance are directly proportional to the dimension. So voltage rating and current rating are directly proportional to dimension square. Whereas the KVA rating is directly proportional to area of the core into area of the window. Area is nothing but dimension square is dimension to the power of 4. And iron loss is equal to copper loss is directly proportional to volume. Volume is dimension whole cube. And we can say this is called the core loss current or winding current, and magnetizing current and the no load current, and the inductance of the inductance and also the magnetizer reactance. All these things are directly proportional to dimension. So voltage rating and current rating are directly proportional to dimension square. KVA rating is directly proportional to area of the core into area of the window. It is directly proportional to dimension to the power of 4. And iron loss is equal to copper loss. It is directly proportional to volume. Volume is dimension cube. And windage current or the winding current or the core current or magnetizing current, and also the no load current and the inductance and the magnetizing reactance, all are directly proportional to the dimension. So voltage rating and current rating are directly proportional to dimension square, and KVA rating is directly proportional to area of the core into area of the window. It is directly proportional to dimension to the power of 4, and iron loss is equal to core loss. It is directly proportional to volume. Volume is dimension whole cube, and a winding current or core current, a core loss component, and this is magnetizing component, and this is no load current, and this is inductance, and this is the magnetizing reactance. All are directly proportional to the dimension. So magnetic circuits. So magnetic circuits means small important formulas regarding this magnetic circuits. MMF is equal to N into I. N is called as the number of turns of the coil, and I is the current is flowing through that coil. So MMF is equal to N into I. And reluctance of the core is equal to L by mu into A. L is called as the mean length of the core, and mu is the permeability of the core, and A is the area of the cross section of this core. And mu is equal to mu naught into mu r. Mu naught is always equal to 4.10⁻⁷ Henry per meter. And energy in the magnetic field. So energy in the magnetic field is equal to half L I square. Half into L into I square is equal to where L is the inductance of the coil and I is the current is flowing through the coil. So half L I square is equal to half into MF into flux. So you can go for this formula also. If you do the rearrangement, you are going to get the same result. So half into Li square or half into MF into flux. So energy stored in the magnetic field is equal to half Li square is equal to half MF into flux. Is equal to energy stored in the magnetic field. This energy stored in the magnetic field. And the inductance of the coil is equal to N square by R. N is the number of turns of the coil and R is the reluctance of the core on which this coil is wounded. So you can see clearly that inductance of the coil is a function of the permeability of the core. As the permeability of the core changes, the inductance of the coil is also going to get changed. So another important concept regarding the magnetic circuit. So you can see clearly here, as you can see clearly in the circuit, this is called the magnetic circuit. So now I am going to wound a coil on this magnetic circuit on one limb. This is coil having a number of turns of N and I is the current just flowing through this coil. So if you apply your right hand thumb, or you can simply if you curl your right hand fingers in direction of the current and your thumb is going to give you the direction of the flux flowing in this magnetic core. So total MMF is equal to number of turns into current I is equal to HC into LC. So HC is called as the magnetic field intensity in this core and LC is the mean length of the core. So we can say Ni is equal to Hc into Lc or simply H into IL. H into L also you can write anything the same. As I've already told you, Ni is equal to already H is nothing but B by mu. So BC by mu or equivalent BC by mu into Lc. As I've already told you, BC is equal to flux per area. So flux in the core by area of the core Lc. So Ni is equal to phi C into Lc by mu AC. This is called as the simply this is called as the reluctance of the core. Say Ni is equal to flux in the core into reluctance R. So Lc is called as the mean length of this core in this fashion. So therefore Ni is equal to flux into reluctance of the core. So F is equal to N into I. You can write F is nothing but N into I, which is called as the MMF of the core. Because of this only the flux is going to get produced in the core, and phi C is called as the flux in the core. And R is called as the reluctance of the core, and Lc is called as the mean length of the core, and mu is called as the mu naught into mu R, where mu naught is equal to 4 pi into 10 to the power of -7. So F is called as the MMF of the core, phi C is called as the flux in the core, R is called as the reluctance of the core, and Lc is called as the mean length of the core, and mu is equal to mu naught into mu R, where mu naught is equal to 4 pi into 10 to the power of -7. So now we will discuss about the Faraday's law. Faraday's law is very much important. So say a magnetic core and I am going to hold one on the limb with a coil of N turns and I am going to induce a current of I of t, supply voltage of V of t. As you apply the right hand, you have to curl your right hand fingers in the direction of the current. The thumb is going to give the direction of the flux. So overall flux linkage is equal to lambda is equal to N into phi, where phi is the flux linkage of because of one turn. So as there are N turns, so N into phi is called as the overall flux linkage. And the rate of change of flux linkage is equal to d by dt of lambda, or simply d by dt of N into phi. As N is a constant, you can take it outside the differentiation. So N into d phi by dt is called as the rate of change of flux linkage is called as the amount of EMF induced in a coil, which is equal to V of t is equal to N into d phi by dt, because both are same polarity. So V of t is equal into d phi by dt. As I already told you, flux in the core is equal to number of turns Ni by R. So phi is equal to Ni by R. R is equal to L by. So V of t is equal to N square A mu by L into di by dt. As you can see clearly, only I is a function of t, so di by dt. The remaining thing is called as the inductance. So N square by R, L by mu A. So this is called as the inductance. So L into di by dt. So V of t is equal to L into di by dt. L is equal to N square by R. So L is equal to N square by R. R is equal to L by mu A. So we can say simply that the rate of change of flux linkage is equal to voltage induced. V of t is equal to d by dt of N into phi. So as N is a constant, you can take it outside the differentiation. So V of t is equal to N d phi by dt. As phi is equal to Ni by R. So therefore simply we are going to get simply N square by R into di by dt. As I have already told you, N square by R is nothing but N square by R is called as inductance. So V of t is equal to L into di by dt. So this is called as a voltage in the amount of induced is another expression. L is equal to L square by R and R is equal to L by mu A. So now expressions for the self-inductance. So expressions for the self-inductance now we are going to study. So now you can see clearly this is a magnetic circuit and I am going to wound a coil of N turns on this limb. So it is now I am going to pass a current of I through this coil. As if you curl your finger, right hand fingers in the direction of the current, the thumb is going to give the direction of the flux. So flux is always directly proportional to current I. I have already told you, as the current increases, the flux is also increases. So when core is not saturated, means core is operating in the linear portion. This is only true only when the core is not operating in the saturation region. So when the core is not saturated, means operating in the linear portion, only then only this is applied. So whenever the core is not saturated or whenever the core is operating in the linear region, then this is always correct. Actually here it has to be overall flux linkage is directly proportional to current I. So overall flux linkage is always directly proportional to current I. So overall flux is nothing but N into phi is equal to L into I. So N into phi is equal to L into I. So overall flux linkage is always directly proportional to I. If you remove the proportional constant, we have to introduce the self-inductance of L. So N phi is equal to L into I. So phi is equal to Li by N. So this is also another formula. So flux is equal to Li by N. So N phi is called as the overall flux linkage, which is equal to lambda, and L is called as the coefficient of the self-inductance. And if you want to find what is the unit of the inductance, self-inductance, which is simply, you can see here, this is called as a Weber turns per ampere. So Weber turns per ampere. Weber is the unit of the flux and turns the unit of the number of turns, and current the unit is ampere. So L is equal to Weber turns per ampere is nothing but Henry. So Ni is equal to R into phi, or Ni is equal to phi into R. So Ni is equal to R is nothing but L by mu A. Mu is nothing but mu naught mu R into A. So by phi. So now if I take here if I take N and if I divide by I, we are going to get phi by I into L by mu naught mu R A. Again do the multiplication by N times. We are going to be on both sides. N square is equal to N phi by I into L by mu naught mu R A. So here N square by R. So this is R. So this is called as the R. So this is called as R. So L is equal to N square by R is equal to N square into L. R is nothing but L by mu A. L by mu naught mu R into A. So simply L is equal to N square by R. R is equal to L by mu A. Or simply I have already told you, L is another formula. Simply I have already told you the another unit of flux is, I have already told you that phi is equal to Li by N. So phi is equal to Li by N. So all these forms I have already told you. So L is equal to N square by R. So this is N square by R. N square by R. So L is equal to N square by R. Another formula which is equal to N phi by I also you can write. So L is equal to N square by R is equal to N phi by I. Anything is correct. Because N square by R is equal to N phi by I. N phi by I is nothing but L. So N phi is equal to L into I. I have already told you. Overall flux linkage is equal to N phi is equal to Li. So do the differentiation of the both sides. N into dpi by dt is equal to L into di by dt. And keep negative on the both sides. Minus N divided by dt is equal to minus L di by dt. Minus N divided by dt is nothing but voltage induced E of t is equal to minus L di by dt. So if I want L is equal to minus E of t by di by dt. So these are the different formulas of the self-inductance. So L is equal to, simply remember this formula, L is equal to N phi by I or N square by R or minus E of t by di by dt. So these are different formulas. So L is equal to N phi by I or N square by R or minus E of t by di by dt. So these are two different expressions of the self-inductance. So now we'll discuss the expressions for the mutual inductance. Mutual inductance. Suppose this is the magnetic core. This is the magnetic core, and here I am going to own the two coils. Primary coil of N1 turns, under coil of N2 turns. So this primary coil I am going to connect with supply voltage, variable supply voltage. So the supply voltage is going to send a current of I1 to this primary coil. So if you curl your right hand fingers in the direction of the current, then you can see the flux is going to produce in the core in this direction. So as the secondary side is open circuit, a voltage is going to get induced across this N2 turns, because this flux is going to pass through these turns, it is going to cut through these coils. So therefore we can say whenever there is a rate of change of flux in a coil, the voltage is going to get induced across this coil. Then what is the amount of voltage induced, which is equal to, I already told you, the total amount of flux linkage with the secondary coil, which is nothing but the total number of flux linkage with the secondary coil is equal to Nt into phi1, where phi1 is the flux produced due to one turn of the primary. So N2 into phi1 is called as the overall flux which is induced in the secondary coil. So N2 into phi1 is directly proportional to current I1, because as the current I1 increases, this flux phi1 increases. As the flux phi1 increases, the product N2 into phi1 is also increases. So N2 into phi1 is directly proportional to I1. So if you remove the proportionality constant, you are going to get N2 into phi1 is equal to M into I1, where M is equal to Nt into phi1 by I1. So M is equal to N2 into phi1 by I1. As I already told you, phi1 is equal to N1 I1 by R. So now R1 is equal to L1 by mu into A. So N1 I1 mu naught mu R A by L1. So what is the value of phi1 by I1? Phi1 by I1 is nothing but N1 by R. N1 by R is nothing but L1 by mu naught mu R A. So you can substitute in this formula. You are going to get N2 into phi1 by I1 is nothing but simply I1 by I1 is same value we will substitute here. We are going to get N1 into mu naught mu R A by L1 is nothing but N1 N2 by R is equal to M. So M is equal to N1 N2 by R. So these are different formulas of L. So M is nothing but here N2 phi1 by I1 or N1 N2 by R. So these are the two different formulas. Also here overall flux linkage is equal to simply I have already told you that M1 I1 is equal to N2 phi1. These things I have already told you. So M1 I1 is equal to N2 phi1, or simply N2 phi1 is equal to M into I1, or N2 phi1 is directly proportional to I1. So N2 phi1 is equal to M into I1. To do the definition of the dt on both sides, we are going to get M into di1 by dt is equal to N2 into phi1 by dy1 by dt. Keep a negative on the both sides, and this is called as a voltage induced in the secondary coil. So EM is equal to minus M di1 by dt. So this is called as the induced voltage in the secondary coil is equal to minus M di by dt. So M is equal to minus EM by di1 by dt. So these are the three different formulas. M is equal to N2 phi1 by I1 or N1 N2 by R, or simply we can say that minus EM by di1 by dt. So these are the three different formulas. So M is equal to N2 phi1 by I1. So these are the three different formulas. M is equal to N2 phi1 by I1 or N1 N2 by R, or minus EM by d M into di1 by dt, or M is equal to minus EM by di1 by dt. This is called minus EM by di1 by dt. So these are the two different expressions of the mutual inductance. So now we will discuss another concept of derivations. So I have already told you flux is equal to Ni by R. R is equal to L by mu A. So if we do the rearrangement, we are going to get Ni mu A by L. So magnetic flux density is equal to flux per area. So as I have already told you, flux per area. So flux per area is nothing but you are going to get mu into Ni by L. So here mu into Ni by L is called as H. So mu into H. So B is equal to flux per area is equal to, you are going to get mu into H. H is equal to Ni by L. N is the number of turns of the primary coil, I is the current of the coil, and L is the mean length of this core. So as I have already told you, now I am going to cut this core into small part. So I am going to remove small part of this core. This length is having the length of Lg. Lg is the length of this air gap, and Lc is the mean length of this core. So now I want to find what is the reluctance of this core and the reluctance of this air gap. Reluctance of this core is equal to Lc by mu naught mu R into A, whereas Rg is equal to Lg by mu naught into A, because mu R is equal to 1 for A. So we can see clearly that mu naught is very less when compared to mu naught into mu R. So Rg is always greater when compared to Rc. So Rg is always greater than Rc, means air gap reluctance is always greater than the core reluctance. But that is the reason always flux try to prefer to the core. Always flux prefer to pass through core rather than the air gap. So now magnetic flux density. So magnetic flux density is equal to flux per area in the core and the magnetic flux density in the air gap is called flux per area. As both are same, so we can say that both are equal. So magnetic flux density in the core is equal to magnetic flux density in the air gap, because flux per area is same in both the cases. So magnetic flux density in the core is equal to magnetic flux density in the air gap. So now what is the value of HC? SC is equal to BC by mu, and HT is equal to BG by mu naught. Because BG is equal to BC, both are same, but you can see clearly mu is very higher. So therefore overall ratio will be less. So therefore HC is always less when compared to HG. So therefore HG is always greater than HC, means you can say magnetic field intensity in the air gap is always higher than the magnetic field intensity in the core, whereas the magnetic flux density is same in both the cases. So if you want to find what is the overall flux, flux is equal to Ni by overall reluctance. Reluctance is nothing but the addition of these two things, which is Rc plus Rg. So if you do the simplification, we are going to get Ni is equal to phi into Rc plus phi into Rg. If you apply the MMF rule, if you apply the Ampere's rule, we are going to get Ni is equal to Hc into Lc plus Hg into Lg. I have already told you Hg into Lg is always greater than the Hc into Lc. So Hg into Lg is always greater than the Hc into Lc, because Hg is very higher. Hg is very higher when compared to Hc. So Hg into Lg is always greater than the Hc into Hc. Suppose there is a small amount of core, and for this core I am going to mean the number of turns of coil of turns N. As the current I of t is passing through this coil, it is going to increase the voltage of E of t. As this passes through coil, it is going to produce a flux phi. So flux phi is equal to N into I of t by R, or simply we can say that N into I of t by R is nothing but I have already told you flux is equal to Ni by R, and these things I have already told you. Flux is equal to Ni by R, and the current is a function of time, so N into I of t by R. Yet I am going to assume that I of t is equal to I naught sin omega t. If I am going to assume the current is a sinusoidal waveform, IN is equal to I naught into sin omega t, then you can substitute in this above formula. I of t is equal to N into, in place of I of t substitute I naught into sin omega t by R. So this N into I naught by R is called as the maximum flux, so phi n into sin omega t. Then what is the EMF induced? E of t is equal to N d by dt. Or you can say d by dt of N phi. As N is a constant, take it outside. N into d by dt. For phi is nothing but this formula. So therefore phi n into sin omega t. So dy by dt I can write in another two formats, which is dy by di into di by dt. So dy by di into di by dt you can write in this fashion also. We are going to get same dy by dt. So dy by, see, N into dy by di is called as L. So L into this is called as di by dt. This is called as di by dt. So L is equal to N into dy by di. So in linear region, I have already told you dy by di is equal to phi by I in a linear region. So therefore L is equal to N phi by I is equal to N into, as already we know, phi is nothing but Ni by R. So I cancels, we are going to get N square by R. R is equal to L by mu A. So L is equal to N square mu A by L is nothing but L is equal to N square by R. So now I want to know how much amount of power consumed by this core. I want to figure out. Power is nothing but voltage into current. So P of t is equal to V of t into I of t. But V of t is nothing but N into d by dt into I of t into I of t. So what is the energy consumed by the core? Energy is equal to power into time. So energy is equal to integration of power into time. So power is nothing but N d by dt into I of t into dt. Power into dt. So power into time is nothing but energy integration. So power is nothing but N d by dt into I of t into dt. So dt cancels, we are going to get N I of t into, see, flux. As I have already told you, flux is equal to B into A. A is a constant, so take it outside. So B is a variable, so dB. So therefore A into dB. So d phi is equal to A into dB. So now, as I have already told you, I of t is nothing but, I have already told you, H is equal to Ni by L. H is equal to Ni by L. So HL is equal to N into I. So I is equal to HL by L. So N cancels. We are going to get simply HL A into dB. So here L and A are constant. The main length of the core and area of the core is a constant. Take it outside. So A into integration of H into dB. A into L is called as the volume of the core. So volume of the core into. So you can say This is the volume of the pore into integration from B1 to B2 H into dB. So this is called as the joules. Energy is always in terms of the joules. So this is called as the area of the pH loop. So this integration is called as the area of the pH loop. So this integration is called as the area of the pH loop. So if you want overall, if you want to know the overall energy consumed by the pore is equal to volume of the pore into area of the pH loop. So listen carefully. If you want to figure out the amount of overall energy consumed, which is equal to volume of the pore into area of the pH loop, its unit is always equal to joules. So if you want to find what is the hysteresis losses, hysteresis losses is equal to, here we are going to take in this format, which is equal to volume of the pore into integration of B1 to B2 H into dB by time t. So this is nothing but power. So power is equal to energy by time. So energy by in a one time period. So 1 by 2 is nothing but frequency. So if we solve this one, we are going to get kh into f into b into b naught to the power of x, where pH is called as the energy loss in one cycle, or it is also called as the hysteresis losses. The amount of energy loss in one cycle is also called as the hysteresis losses. Therefore, the amount of energy loss in one cycle is called as the hysteresis losses. Amount of energy loss in one cycle is called as the hysteresis losses, where x is nearly equal to 1.6. So we can say power is equal to energy loss in one cycle or one time period. That is, it is in this format, h into f into b into the power of x, b to the power of x. X is always nearly equal to 1.6. Where pH is called as the hysteresis losses or energy loss in one cycle or one time period. So now we will understand the per unit concept. Per unit concept. So per unit concept is nothing but jet per unit is equal to actual value by base value. Jet per unit is equal to actual value by base value. Actual value is jet by jet base. So jet base is nothing but V base by I base. Jet base is equal to V base by I base. So if we do the rearrangement, we are going to get jet into IB by VB. So jet per unit is equal to jet into IB by VB. So do the multiplication of IB on, do the multiplication of VB on numerator and the denominator. We are going to get jet into VB IB by VB square. So this is called as the rated value power, rated base power, and this is called as the rated voltage also, or simply we can say that this is called as the base rated by voltage rated or base voltage. So base complex power by base voltage. So simply jet current is equal to jet into MVA rated by KV rated whole square. So these are the different formulas. So simply jet per unit is equal to actual value by base value. So we can write jet base is equal to V base by I base, or simply we can write jet base is nothing but another format also, which is equal to VB base whole square by S base. So you can go for anything. We are going to get the same result. So per unit is equal to actual value by base value. Z base is equal to V base by I base, or V base whole square by S base. So you can go for any of the thing, you are going to get the same result. So in this fashion, you are going to get a different formulas. So Z point is called as a per phase value in machines in star connection and also in the delta connection. So per phase values in machine and star connection and also in the delta connection. So Z point is equal to Z into MV divided by KV base and the whole square. These are the formula. So Z point is called as a per phase value in machines for star connection or the delta connection. So per phase values in machines in star connection and also in the delta connection, because wires are connected in either star connection or the delta connection. So these are the per phase values. These are the per phase values in the machines, either star connection or the delta connection. So this formula belongs to the per phase value. Per phase values in machines for star connection or the delta connection. We have to always use the per phase values. We have to always use the per phase value. This is the per phase values in the machines for star and delta connection. You always have to use the per phase values. So in the star connection, star connection, Z current is equal to Z into, here star connection per phase. Then what is the per phase power? Per phase is equal to MVA by 3, overall by 3, and per phase voltage is nothing but line voltage by root 3 whole square. So if you solve this one, we are going to get same thing, Z into MVA by line voltage whole square. So listen carefully. In a star connection, we have to use the per phase values above and below. The per phase is nothing but line voltage by root 3. The phase voltage means the phase voltage base value is equal to line voltage by root 3, and this is per phase. We have to find the base value of the per phase, which is overall by 3. So if you solve this one, we are going to get like this. In delta connection, so Z point is equal to Z ohm into per phase value is nothing but MVA by 3, and here line voltage is equal to phase voltage. So just use the KVL sphere. So if you solve this one, we are going to get in this value. So this is the thing that you always have to remember. So whatever the Z current formula, that is all as a per phase value. So that is the per phase values in machines, either star connection or delta connection. Means you always have to use the per phase values. Only the per phase value we have to use, not the overall value. Just use the per phase values. For star connection, this is by 3, and this is per phase is nothing but line by root 3. Whereas here per phase is again by 3, and here line is equal to phase voltage. So this is the formulas for both star connection and the delta connection for the per phase per unit values. For the Z current for the each and every phase. Z current is equal to Z by Z base. Actual value by Z base. So actual value is nothing but R plus Jx. Both are in ohms. R plus Jx by Z base. So now you divide this Z base on both sides. For the two parts, we are going to get Z current is equal to R current plus X current. Where R current is equal to R by Z base and X current is equal to X by Z base. So R current is equal to R by Z base. So R by Z base we can write V base by I base. So here we can say R by Z base is nothing but V base by I base. So we are going to get simply I base into R by VB. Do the multiplication of IB on both sides. On the numerator denominator we are going to get IB square R by VB IB. So this is called as the R current is equal to, this is called as the full load copper loss. This is called the full load copper loss by rated VA or rating of transformer. So this is called the full load copper loss by rated VA or rating of transformer. It is called as the full load copper loss per unit value. This ratio is called as the full load copper loss by rated VA rating of transformer. It is called as the full load copper loss per unit value. So this is called as the full load copper loss by rated VA or rating of transformer. So R per unit is equal to ratio of the full load copper loss by rating of transformer or rated VA. It is nothing but full load copper loss in per unit. So R per unit is always equal to full load copper loss in per unit. The per unit value of transformer parameter is same in primary as well as in the secondary side. The per unit value of transformer parameter is same in primary as well as in the secondary side. The per unit value of transformer parameter is same in primary as well as in the secondary side. The per unit value of the transformer parameter is same in both the primary as well as in the secondary side. The per unit value of the transformer parameter is same in primary as well as in the secondary side. So the per unit value of the transformer parameter, is same in primary as well as in the secondary side. So now we'll discuss some more important concepts regarding the transformers. So this is we can see a core of a transformer. So here we are going to use a primary winding, and here we are going to use the secondary winding. So this is called the primary coil and the secondary coil. So primary coil of turns N1, secondary coil of turns N2. So it is basically a single phase. Let me assume the reading of this transformer is SVA, and the induced voltage ratio, which is E1 by E2. So E1 by E2 is called as the E1 is the induced voltage in the primary, and E2 is the voltage induced in the secondary. So now this I1R is called as the rated current flowing in the primary winding, and I2R is called as the rated current flowing in the secondary winding. So I1R is called as the rated current flowing in the primary winding, and I2R is called as the rated current flowing in the secondary winding. So now, as I already told you, induced voltages, which are the RMS value, E1 is equal to 4.44 N1 F phi M, whereas E2 is equal to 4.44 N2 phi Fm. So if you simply take carefully, E1 by N1 is equal to E2 by N2. It means that voltage per turn which is induced is same in both the primary and also the secondary. So the voltage per turn which is induced in primary and also secondary is always same. The amount of voltage induced per turn which is induced in both the coils is always same. The voltage, you can say, the amount of voltage induced per one turn is same in both the primary coil and also in the secondary coil. So E1 by N1 is equal to E2 by N2. If you want to find what is the rated current in the primary winding, which is equal to S by E1, and if you want to find what is the rated current in the secondary winding, I2R is equal to S by E2. So by this you can know the rated currents in the primary coil and also in the secondary coil. Whereas for three-phase transformer, this is the formula that you always have to use for three-phase transformers, but not for single phase. S is equal to root 3 VL IL is equal to 3 into V phase into I phase. So this is the formula that you always have to remember for three-phase transformers. S is equal to root 3 VL. S is equal to root 3 into VL into IL is equal to 3 into V phase into I phase. Whereas, as I have already told you, magnetic flux density is equal to flux per area. So if you want the maximum value, the maximum value of the flux density is equal to maximum flux per area, as there is a constant. So if you want Bm maximum B, then you need the maximum flux also. So maximum magnetic flux density is equal to maximum flux per area. So N1 and N2 are always integers because they are terms. They will never be fractions. They will always be integers. Suppose if you are not going to connect any load, means the load we are not going to connect, then you see what is going to happen. See now the primary winding is a core of a transformer, the single phase transformer rating of SVA with the voltage ratio E1 by E2. So this is the primary winding of turns of N1, secondary winding of turns of N2. So primary winding I am going to connect to a supply voltage of E1. As there is no load, still a small amount of current is going to draw by this primary coil. A small amount of current I know. This is called as a no load current because we have not kept any load, but still a small amount of current is drawn by this primary coil. It is called as a no load current I know. See, I naught is nearly 1% of full load current. Suppose if you keep a full load, the amount of current drawn at that time, it is very high. So this is only 1% of that full load current. So I naught is equal to only 1% of the full load current. So now if I draw the equivalent circuit diagram of a transformer at no load condition, this is what I am going to get. So this is the supply voltage across the primary side. So therefore this is a supply voltage plus or minus E1 and this is a shunt branch. This is R0 and this is XM. R0 is called as a core resistance and XM is called as a magnetizing reactance. So this is IW or IC. You can go for anything. And this is IMU and this is I0. IW or IC is called as a core loss component and IMU is called as a magnetizing component and I0 is called as a no load current. As the circuit is open circuit, so this current is always equal to 0 because the secondary current is 0, so I2 dash is also equal to 0. Only I1 is going to present, I1 is equal to I0 in this case. So if you draw a phasor diagram, see this is the induced voltage in the primary winding. Always the flux is going to lag the primary induced voltage by 90 degree. And E1 and E2 always in the opposite phase. And you can see E1 and E2 are always opposite the phase of each other. This is E1 and this is the E2. So you can see clearly that E1 and IW both are across the resistor load. So both are in phase. So this is IW. Whereas IMU, you can see clearly IMU for inductor. So current is going to lag the voltage. So current is going to lag the voltage by 90 degree. This is IMU. So because of IMU only flux is produced. So both are in a same phase. So now whereas I0 is a vector sum of IW and IMU. So IW and IMU is the vector sum, we are going to get I0. So this is called as a power factor angle at no load. So the phase angle between the supply load and the supply current at no load is called as the power factor angle. This is the phi naught. So always IMU is always greater than the IW because see IMU is always greater than the IW. That is the reason phi naught is very high. Phi naught is very high because this IMU is very high. So vector I naught tends to towards direction of IMU. So therefore IMU is always greater than IW. So therefore phi naught is very high. It is nearly equal to 90 degree but not 90. So therefore IMU is always higher than the IW. So if you want to find how much amount of power consumed by this circuit at no load condition, because a primary one is going to draw a small amount of current, it means it is going to accept some amount of power. So P naught is equal to voltage E1 into supply current I naught into cos of phi naught. So E1 into I naught into cos of phi naught. Or simply we can write in another format. I naught into cos phi is nothing but I naught into cos phi is nothing but IW. So E1 into IW you can go for anything, or E1 square by R0 also we can write. So E1 square by R0 also we can write, because only the resistor R0 is going to consume the power but not XL. So therefore P is equal to E1 into I0 into cos phi naught, or E1 into IW, or E1 square by R0. You can go for any of this formula. So therefore now, what is the value of I0? I0 by Pythagoras theorem, I0 is equal to under root over IW whole square plus I0 square. So IW is equal to I0 cos phi naught and I0 is equal to I0 sin phi naught. Plus R0 is equal to simply R0 is equal to E1 by IW. This is called as a core loss resistance. The core loss is always independent of load. So core loss is always independent of load. See, core loss is never dependent on load. No matter whatever the load, core loss is always constant. So core loss is independent of the load. So cos phi naught is called as a no load power factor, because there is no load, because we have not kept any load at the secondary. So this is called as a no load power factor, and phi naught is nearly equal to 90 degree, but not exactly. So now we will see the different views. So here, this is the transformer. I am going to remove the shunt branch. I am going to neglect the shunt branch of this transformer. So you can see clearly this is the N1 turns and this is the N2 turns. We are going to assume this as the ideal transformer. This is a basically ideal transformer. But here the primary winding will have small amount of resistance and also small amount of reactance. And the secondary winding is also having a small amount of resistance and a small amount of reactance. So now I am going to connect a supply voltage of V1, and now there is a load of ZL. So this is the current I1 and this is the current I2, and this is the load voltage V2. V2 is the voltage across the load ZL, and the power factor of the load is cos phi. So now what I am going to do is basically I am going to shift the secondary to the primary side. So then what I am going to get R01, X01, and similarly the ZL dash. But the power factor of the load will be always same. Whether you shift it to the primary side also, the power factor of the load will be always equal to again cos phi. So R01, X01, and this is V2 dash and ZL dash, and the supply voltage V1. So I have shifted all these things to the primary side. So R01 is equal to R1 plus N1 by N2 whole square into R2, and X01 is equal to X1 plus N1 by N2 whole square into H2. Similarly, ZL dash is equal to ZL into N1 by N2 whole square. So similarly, now V2 dash is equal to V2 into N1 by N2. So this is a thing that you always have to remember. So R01 is equal to R1 plus N1 by N2 whole square into R2. X01 is equal to X1 plus N1 by N2 whole square into H2. And ZL dash is equal to ZL into N1 by N2 whole square. And V2 dash is equal to V2 into N1 by N2. So this is the things that you always have to remember. Even if you don't remember this also, just do the multiplication of I1 into ZL dash, you are going to get V2 dash. So this is the circuit diagram we are going to get if you refer back to the primary side. This is the current I1. So now if you just do the algebraic one, not the power factor values, just the magnitude values, if I am going to consider only the magnitude values, if I am going to consider, then V1 is nearly equal to V2 dash plus I1 into R01 cos phi plus or minus X01 sin phi naught. So remember, just I am going to assume only the algebraic values, not the phasor values. So V1 is nearly equal to V2 dash plus I1 into R01 cos phi naught cos phi plus or minus X01 sin phi. So this is a very important formula. So this is only algebraic formulas. This is only algebraic values. So V1 is nearly equal to V2 dash plus I1 into R01 cos phi plus or minus X01 sin phi, where phi is the power factor of the load. So V1 is nearly equal to V2 dash plus I1 into R01 cos phi plus or minus X01 sin phi. So here phi is called the power factor of the load. So the plus is used for lagging load and minus is used for the leading load. So we have to use plus for lagging load and minus for the leading load. So this formula is only for the algebraic values. Just we will get only the algebraic values, means the magnitude values, but not the phasor values. So therefore now listen carefully. As I have already told you, I1 by I2 is equal to N2 by N1, because the MMF is always equal. So I1 N1 is equal to I2 N2. So I1 N1 is equal to I2 N2. So I1 N1 is equal to I2 N2 means I1 by I2 is equal to N2 by N1. Suppose if I shift to the secondary side, if I shift the primary to secondary side, what is going to happen now? We will see. So therefore now this overall, see the current is I2, so current is I2, this is V2, this is ZL, and is the cos phi is the power factor of the load. So now listen carefully, then this is called as R0 to X02. So R02 is equal to R2 plus N2 by N1 whole square into R1, whereas X02 is equal to X2 plus N2 by N1 whole square into, so X02 is equal to X2 plus N2 by N1 whole square into X1. So now if I do the V1 dash is nothing but N2 by N1 into V1. So V1 dash is equal to N2 by N1 into V1. So this we are going to get. So this is the circuit that we are going to get now. So if you apply only the magnitude values, then V1 dash is nearly equal to V2 plus I2 into R0 to cos phi plus or minus X0 to sin phi. So plus is used for the lagging load and minus is used for the leading load. Only this is for only the magnitude values. I've already told you N1 I1 is equal to N2 I2. So therefore I1 by I2 is equal to N2 by N1. This is the basically a circuit. R1 X1 I1 N1 turns N2 turns R2 X2 current I2 V2 ZL cos phi is equal to power factor. This is an applied voltage P1. So this is the thing that you always have to remember the concepts. So now we will discuss the effect of copper resistance and leakage drops. So we will discuss now effect of copper resistance and the leakage drops. Suppose there is a transformer, single phase transformer of primary coil and secondary coil. So this is a ideal, this part is ideal transformer. So this is E1, E2. So plus or minus E1, plus or minus E2. This is N1 and this is N2. So this primary coil is going to have small amount of reactance and also small amount of resistance and small amount of reactance. The secondary winding is also going to have small amount of resistance and reactance. So primary we are going to give supply voltage of V1. And secondary we are going to give a supply the load of V2. So therefore this is V1, R1, JX1, I1 plus or minus E1, N1, N2 plus or minus E2, R2, JX2, I2, load plus or minus V2. So what is Z1? Z1 is equal to R1 plus JX1, Z2 is equal to R2 plus JX2. So Z01 is you are going to refer the secondary to primary, which is simply R1 plus N1 by N2 whole square into R2 plus J times of X1 plus N1 by N2 whole square into X2. Similarly, if you refer the primary to secondary, we are going to get Z2 is equal to R2 plus N2 by N1 whole square into R1 plus J of X2 plus N2 by N1 whole square into X1. So now if I am going to draw the phasor diagram for a lagging load, I am going to draw the phasor diagram. See, this is the voltage V2 across the load. As the load is a lagging load, so I2 is going to lag the load voltage V2 by phi 2. So therefore, I2 is going to lag the V2 by phi 2, angle of phi 2. I am going to assume phi 2 is the power factor of the load, or you can use phi also, anything nothing will happen. I have assumed phi 2 is the power factor of the load. So it is going to lag V2 and I2 is going to lag V2 by angle phi 2. So now, as there is a R2 and JX2, so R2 means you can say that the current and voltage across the resistor R2 are in phase. So current and voltage are in phase in the resistor. So therefore, if this is R2 means this will be I2 into R2. Whereas in the inductor, the current is going to lag the voltage by 90 degree. So current is going to lag the voltage by 90 degree. So therefore, here we have to use the voltage. This is nothing but simply we are going to get, this is called as I2 into X2. So if you do the addition of all these three vectors, we are going to get E2. So this is called as the E2 voltage. And I have already told you E2 and E1 always opposite of each other. So the angle between them is 180 degree. So this is I1. As I have already told you, the flux in the core is going to lag even by 90 degree. So what I have not shown here. So suppose let me assume suppose the flux is going that I have already told you that flux is going to lag even by 90 degree. So because of that, I0 is also going to flow. As I have already told you, I0 is going to flow somewhere here. So I0 is always going to flow somewhere here. And because of that, there is also now this is the current I2, and I2 and I2 dash are always in opposite of each other. They have a phase difference of 180. So this is I2. So I2 dash and I0 is nothing but we are going to get I1. So this is the value of the I1. So this is the value of the I1. So I2 dash and I0 reflection is nothing but I1. Therefore, this is the value of the current I1. So now this current I1 is going to pass resistor R1. So both are in phase. So I1 into R1, and also in the inductor you can say that the voltage is going to lead, or current is going to lag the voltage by 90 degree. So voltage is going to lead. So this is the voltage that is going to lead here. So current is going to in this direction, voltage is in this direction. So voltage is going to lead the current by 90 degree. So this is I1 into X1. So if you do addition of all these three vectors, we are going to get the supply voltage V1. So now this is the overall phasor diagram. So you can see clearly we can say that the power factor angle between the supply voltage and the supply current, which is V1 and I1, the phase angle is phi1, and the phase angle between the load voltage and load current, V2 and I2, is phi2. The angle between the power factor angle between the supply voltage and supply current, V1 and I1, is phi1, and the angle between the load voltage and load current, V2 and I2, is nothing but phi2. So now I have already told you E1 and E2 vectors are opposite of each other, means 180 degree between them, and similarly I2 dash and I2 are having the phase difference of 180 degree between them. And I have already told you V1 bar is equal to I1 bar Z1 bar plus V1 bar. Similarly E2 bar is equal to I2 bar Z2 plus V2 bar. So V1 bar is equal to I bar Z1 plus V1 bar. Similarly E2 bar is equal to I2 bar Z2 plus V2 bar. So this is the formulas that you have to remember by just using the vector KVL. So now E1 by E2 is always equal to N1 by N2. So E1 by E2 is nothing but N1 by N2. And also I already told you that N1 here in this case now N1 E2 dash is equal to N2 I2. So remember here N1 I2 dash is equal to N2 I2. So N1 I2 dash is equal to N2 I2. So what is Z01? Z01 is nothing but simply N1 by N2 whole square into Z02, or Z02 is equal to N2 by N1 whole square into Z01. So very simple. Z01 is equal to N1 by N2 whole square into Z02, or Z02 is equal to N2 by N1 whole square into Z01. So very simple thing. So now basically we are going to study about the approximate voltage drop in a transformer. So what is the approximate voltage drop in a transformer? This concept now we are going to study. So this is a single phase transformer with two windings, primary and the secondary. So this part is basically an ideal transformer. So this primary winding will have an induced voltage of E1 plus or minus E1, and the secondary winding will have an induced voltage of plus or minus E2. The primary number of turns are N1 and secondary number of turns are N2. So basically any transformer winding will have a small amount of resistance and reactance. So let me assume this is R1 and X1. Similarly, the secondary winding is also going to have some amount of resistance and reactance, R2 and X2. So now I am going to supply a voltage source of V1 and I am going to apply a load at the secondary side. So this is the V1 and the input current is I1, this is E1, and this is E2, and this is I2, and this is the load which is V2. So power factor of the load I am going to assume this is a cos phi. Cos phi is the power factor of the load. So what I am going to do basically is I am going to shift this circuit, this primary to the secondary side. So if I shift this circuit to the secondary side, then RO2 is nothing but which is R2 plus N2 by N1 whole square into R1. Similarly, XO2 is equal to X2 plus X1 into N2 by N1 whole square. Similarly, this voltage source also we are going to shift to the secondary, which is N2 by N1 into V1. So N2 by N1 into V1. So this is nothing but K. We are going to assume K is equal to N2 by N1. As I already told you, E2 by E1 is equal to N2 by N1, which is equal to K. I am going to assume here. So now if you see clearly, just take the algebraic values, not the phasor values, just take the algebraic values. Then this voltage minus this voltage is nearly equal to, I2. This is the current, secondary side the current is I2. So I2 into RO2 cos phi plus or minus XO2 into sin phi. I am going to take I2 as common. So if I take I2 as common, this is I2 into RO2 cos phi plus or minus XO2 sin phi. If you keep the I2 inside, we are going to get in this matter. So this is only algebraic values are considered, not the phasor values. Only these are the algebraic values are considered, not the phasor values. This is the point that you always have to remember. So plus is the sign. Plus is the sign used for only the lagging type of load, and minus is the sign for the leading type of load. So what is the voltage regulation? The voltage regulation concept is no load voltage minus load voltage by no load voltage into 100. So the percentage of regulation is equal to no load voltage minus load voltage by no load voltage into 100. See, no load voltage minus load voltage is nothing but the drop across the, we can say the drop across the RO2 and the XO2, which is nothing but simply we can say that K into V1 minus V2 by K V1 into 100. See, suppose if you are opening the circuit, if you are opening the load, it means what is the no load voltage, which is nothing but here K into V1. So see, K into V1 is the no load voltage. If you keep a load, the load voltage is V2. So K1 minus V2 by KV1 into 100. Already we know the value of KV1 minus V2, which is I2 RO2 cos phi plus or minus I2 XO2 sin phi by K into V1 into 100. So now I2 RO2 by KV1 is nothing but which is VR cos phi plus or minus, this is I2 XO2 by KV1 is nothing but Vx sin phi. So therefore simply this is called as the percentage of voltage regulation is equal to percentage of voltage drop across the internal resistance and the reactance. So this is called as the percentage of voltage regulation is equal to percentage of voltage drop, which is simply we can write percentage of voltage regulation is equal to VR into cos phi plus or minus Vx into sin phi. So percentage of voltage regulation is equal to percentage of voltage drop. So this is the point that you always have to remember. So whenever we are opening the load, the voltage is KV1, and if you keep a load, the voltage is V2. So K1 minus V2 by K1 into 100. We know this value. Just substitute here and do the division. This is I2 RO2 by K1 is nothing but VR cos phi plus or minus I2 XO2 by K1 is nothing but Vx sin phi. So percentage of voltage regulation is equal to percentage of voltage drop across the, we can say that RO2 and the XO2. So VR is called as a percentage voltage drop due to RO2, and Vx is called as a percentage voltage drop due to XO2. So this is the point that you always have to remember. So therefore VR is nothing but it is a voltage drop due to the RO2, and Vx is called as a percentage voltage drop due to XO2. So VR is called as the percentage voltage drop due to RO2, and Vx is called as a percentage voltage drop due to XO2. So now the next concept is nothing but dependency of transformer parameters and the linear dimension. So dependency of transformer parameters and the linear dimension now we are going to study. So this is the core of a transformer. Here it is a primary winding and here it is a secondary winding. Primary winding is of number of turns of N1 and secondary winding is of a number of turns of N2. This is called as the area of the core, whereas this part is called as the area of the window. This is called as the area of the core and this is called as the area of the window. So AC is called as the core cross-sectional area and AW is called as the window cross-sectional area. So AC is called as the core cross-sectional area and AW is called as a window cross-sectional area. Then what is the voltage rating? The voltage rating or the EMF induced across the primary or the secondary, the general equation, the E is nearly equal to the supply voltage is equal to 4.44 NF phi M. So this is a formula that you always have to remember. So E is nearly equal to the supply voltage is equal to 4.44 NF phi M, where phi M is called as a maximum flux density. So maximum flux density is equal to maximum flux is equal to maximum flux density into area of the core. So you can see clearly that the voltage rating is directly proportional to the area of the core. So voltage rating is directly proportional to area of the core. Area means two dimensions, so the linear dimension whole square. So therefore the voltage rating is directly proportional to linear dimension whole square, or simply we can say the voltage rating is directly proportional to area of the core. It means that it is directly proportional to the linear dimension whole square. Only because of two dimensions only we are going to get the area. So now current rating. Current rating means, see, KW is equal to ratio of the total cross-sectional area by the window area. So KW is the ratio of the total cross-sectional area by the window area. So you can see clearly total cross-sectional area by the window area. So what is the total cross-sectional area? See, N1 turns into AC plus N2 turns into AC by AW. We can say that how much amount of space we are using out of the total area AW. This KW is going to tell you how much amount of the window area we are going to use with the help of this winding Right? It is called as the KW. KW is going to tell you how much amount of the window area you are going to use. You are going to use out of the total window area KW. So KW is called total cross section area by the window area, which is N1 into AC plus N2 into AC. N1 into AC plus N2 into AC by AW. N1 into AC plus N2 into AC by AW. So now here current density is equal to current per area. So current density is equal to current per area. So therefore we can see area is common for both the primary and the secondary. So therefore AC is equal to I1 by J is equal to I2 by J. So in place of AC I am going to substitute I1 by J and I2 by J by AW. So already the MMF is always equal. So N1 I1 is equal to N2 I2. So if you solve this one, we are going to get 2 N1 I1 by AW into J. N1 I1 by AW into J. So now we are going to get, if you do simplification, we are going to get I1 is equal to KW into J by 2N1 into AW if you do the rearrangement. So now you can see clearly the current rating is directly proportional to area of the window. So area of the window means it is the linear dimension whole square. So therefore simply we can say that the current rating is directly proportional to window area, whereas the voltage rating is directly proportional to core area, whereas the current rating is directly proportional to the window area. So current rating is directly proportional to window area. It is directly proportional to window area means we need two dimensions. So we need linear dimension whole square. So voltage rating is directly proportional to the core area, whereas the current rating is directly proportional to the window area. So we can say simply the voltage rating and also the current rating is directly proportional to linear dimension whole square. Now what is the KVA rating? So KVA rating is nothing but KVA rating means KVA rating is equal to the product of the voltage rating and also the current rating. So KVA rating means it is a product of the voltage rating and the current rating. So KVA rating means it is a product of the voltage rating and the current rating. So already we know the voltage rating is directly proportional to dimension square, whereas the current rating is directly proportional to dimension square. So if the product of these two things, we are going to get dimension to the power of 4. So we can say simply that KVA rating is directly proportional to AC into AW is directly proportional to linear dimension to the power of 4. So this is the point that you always have to remember. So the voltage rating is the voltage rating is directly proportional to the area of the core. It means that it is directly proportional to linear dimension whole square, whereas the current rating is directly proportional to area window area, it is directly proportional to linear dimension whole square, whereas the KVA rating is directly proportional to AC into AW, is directly proportional to linear dimension over to the power of 4. So now core loss, what is called the core loss? Core loss is also called as the iron loss. It is a summation of the hysteresis loss and also the eddy current loss. So the hysteresis loss and also the eddy current loss is the summation of the hysteresis loss and eddy current loss. So what is the hysteresis loss? The formula is eta into Bm to the power of x into f into volume of the core plus K into Bm square f square T square. So this is the formula of the hysteresis loss and this is the formula of the eddy current loss. So the hysteresis loss is eta Bm to the power of x into f into volume of core, whereas P is equal to K into Bm square f square T square. So this is the formula that you always have to remember. So hysteresis loss is equal to eta into Bm to the power of x into frequency into volume of core plus eddy current loss is K into Bm square f square into T square. So this eddy current loss is almost constant. This eddy current loss is almost constant. So we can say that this is almost constant. So always hysteresis loss is always greater than the eddy current losses. So we can assume that. So as the hysteresis loss is always greater than the eddy current loss, we can assume that the core loss or the iron loss is nearly equal to the hysteresis loss, which is nearly equal to eta into Bm to the power of x into frequency into volume of the core. So we can say that the iron loss or the core loss is directly proportional to the volume of the core. See, volume of a core can be made only with the 3 dimensions, so therefore dimension of the power of whole cube. So we can say clearly that the voltage rating is directly proportional to the area of the core. It means that it is directly proportional to dimension whole square, whereas the current rating is directly proportional to the window area. It is directly proportional to the linear dimension whole square, whereas the KVA rating is directly proportional to the voltage rating into current gradient. So therefore it is directly proportional to the window area into core area. It is directly proportional to linear dimension to the power of 4. Whereas the iron loss is equal to core loss is nearly equal to hysteresis loss. So therefore hysteresis loss is directly proportional to volume of the core. So therefore it is directly proportional to linear dimension over cube. So now let me discuss about the, we can say that it is called as the core loss component current, or simply we can say, we can also call it as the winding current, or simply we can call it as the core loss component of the current. So IW or IC, you can write anything. So the core loss component is equal to, you can say that simply here PI by V1. So therefore PI by V1, because power loss is nothing but power loss by V1. So therefore IW is equal to P1 by V1, because core loss means that the core loss is happening only in the R naught. In the R naught only the core loss is going to happen, because inductor will never absorb the active power. So all the core loss is happening only in this R naught. So therefore IW is equal to P1 by V1. So PI by V1. So it is directly proportional to iron loss is directly proportional to linear dimension volt cube, whereas the voltage rating is directly proportional to linear dimension volt square. So therefore, finally we are going to get IW is directly proportional to linear dimension only. So therefore, we can say that the core loss component of current is directly proportional to linear dimension. Whereas VI, inductance is nothing but inductance is equal to L square by R. L square by R means R is equal to L by mu A, L by mu into A. A is called as the area of the core. Area of the core. So therefore, you can see clearly L is called as the inductance of the coil. So L is directly proportional to area of the core by length. Area of the core is nothing but linear dimension whole square, whereas L means dimension. So only one we are going to get finally, it is the directly proportional to dimension. So simply we can say that the inductance of the coil is directly proportional to linear dimension. Similarly, the magnetizing reactance is equal to 2 pi f into Lm. 2 pi f into Lm. So you can see clearly it is directly proportional to Lm. Lm is directly proportional to dimension. So therefore Xm is also directly proportional to linear dimension. So now I know is called as the magnetizing current is equal to V1 by Xm. So V1 by Xm, V1 is nothing but it is directly proportional to linear dimension whole square by, and Xm is directly proportional to dimension. So only one part we are going to get finally, which is directly proportional to dimension. So now again I naught is equal to under root over I mu square plus IW square. Already I told you I mu is directly proportional to dimension, whereas IW is directly proportional to dimension. So dimension square plus dimension square plus dimension square. Again root we are going to get dimension. So therefore it is also dimension. So we can say simply that finally the I mu is directly proportional to dimension, IW is directly proportional to dimension, I naught is also directly proportional to dimension, L is directly proportional to dimension, and Sm is also directly proportional to dimension. So finally I can conclude that simply the voltage rating and the current rating are directly proportional to linear dimension whole square, whereas the kVA rating is directly proportional to linear dimension to the power of 4, whereas the iron loss or the core loss is directly proportional to linear dimension whole cube, whereas the I mu, IW or IC or I naught and L and Xm, all these things are directly proportional to linear dimension. So now we will discuss about the harmonics in a single phase transformer. See, what are the harmonics that are present in a single phase transformer? Now all these concepts now we are going to learn. The harmonics present in a single phase transformer. Suppose let me take a current I of t which is equal to Im sin omega t plus Im3 sin 3 omega t. So we can say I of t is equal to Im sin omega t plus Im3 sin 3 omega t. So then what is going to happen now? We are going to see what is the nature we are going to get. See, this is called as the Im sin omega t. So Im sin omega t. Im3 sin omega t means, so Im sin omega t, this is the graph we are going to get 3 cycles. So in a given time period, we are going to get 2 cycles. Im3 sin omega t. So if you are going to add these two waveforms, what is going to happen? So you can see clearly here it is a positive, here it is a negative, means overall value will decrease here. Similarly here, if you see clearly, here it is negative, here it is positive. So negative positive means again it will decrease. So you can see clearly this is the graph we are going to get. So this is the graph we are going to get. This is the resultant, which is this is the resultant I of t, which is the summation of the Im sin omega t plus Im3 sin 3 omega t. So this is the graph we are going to get. This graph is called as the flat topped waveform. Flat topped waveform. So flat topped waveform is the waveform we are going to get. This is called as a flat topped waveform. This waveform is called as a flat topped waveform. Whenever I of t is summation of the Im sin omega t plus Im3 sin 3 omega t, we are going to get a waveform. This is called as a flat topped waveform. Suppose if you take a new waveform I of t, it is the difference of this Im sin omega t minus Im3 sin 3 omega t. Then what you are going to get? Then see, this is called as the Im sin omega t. So this is Im sin omega t. Now minus Im3 sin omega t means just reverse of the previous one. So we are going to get like this. So this is called as the simply you can see 3 cycles in a given time period, 1, 2 and 3 cycles. So therefore this is called as a minus Im3 sin omega t. So now we have to add these two waveforms. So here it is positive, here it is positive. So overall value again positive. Here is negative, here negative. Overall value is negative. So you can see clearly you are going to get a peaky waveform. If you add these two signals, we are going to get a resultant signal which is having a peaky waveform. So we are going to get a peaky waveform. So whenever you add the Im sin omega t and Im3 sin omega t, Im3 sin 3 omega t, then we are going to get a flat topped waveform. Whereas if you subtract the Im sin omega t minus Im3 sin 3 omega t, we are going to get a peaky waveform. And always the differentiation of the flat topped waveform, we are going to get the peaky waveform. So the differentiation of the first signal, we are going to get the second signal. So differentiation of the flat topped waveform, we are going to get the peaky waveform. This is a point that you always have to remember. So the differentiation of the flat topped waveform is nothing but peaky waveform. The differentiation of the flat topped waveform is nothing but it is a peaky waveform. So whenever you add the Im sin omega t plus Im3 sin omega t, we are going to get a flat topped waveform. Whereas if you subtract the Im sin omega t minus Im3 sin 3 omega t, we are going to get a peaky waveform. And the differentiation of the first signal, which is equal to second signal, it means that the differentiation of the flat topped waveform is equal to the peaky waveform. So now we discuss some more important points regarding this concept. So now I am going to assume that the flux is sinusoidal. I am going to assume that flux is sinusoidal. The flux in the core is sinusoidal, and the BH loop and the BH curve is a linear curve. See, BH is a linear curve. Then what is going to happen? We are going to see the y-axis is the B and h-axis is the H. So y-axis is the B and h-axis is the H. H is directly proportional to I and B is directly proportional to flux. H is directly proportional to I and B is directly proportional to flux. So now you can see clearly whenever the BH curve is a linear and the flux is sinusoidal, then what is I mu? I mu is called as a magnetizing current. Because of this magnetizing current only the flux is producing. As it is a linear, then as the flux is sinusoidal, then the I mu is also sinusoidal. So therefore, whenever the I mu is sinusoidal, already I have already told you EMF is a function of only EMF is equal to N into d phi by dt. As the flux is sinusoidal, the EMF is also sinusoidal because EMF is depending only on the flux equation. So EMF is equal to N into d phi by dt. Differentiation of sinusoidal signal is again sinusoidal. So EMF is also sinusoidal. Second case, same thing, again flux I am going to assume sinusoidal, but now the BH loop is non-linear because non-linear means it is going to saturate after some time. I have already told you B is directly proportional to flux and H is directly proportional to current. So see, now what you are going to get? Now we are going to get I mu as a peaky waveform. We are going to get a peaky waveform. See, if you want a flux to be sinusoidal, we have to give a magnetizing current which is a peaky nature. Peaky means, I have already told you, peaky means it is going to have huge amount of peak value, because that huge amount of peak value is necessary because there is saturation. For a saturation, you need huge amount of current. If you need huge amount of current, then only we can get a flux as sinusoidal. If you give huge amount of peak value of current, then only we can get a flux of pure sinusoidal. So we can say I mu is a peaky nature. And EMF, I've already told you, it's a function of flux. EMF is equal to N dV by dt. So as the flux is sinusoidal, the differentiation of it is also sinusoidal. So therefore EMF is also sinusoidal. So now the other case is I am going to assume flux as sinusoidal, but the BH is having some hysteresis loop. Hysteresis loop means we can see I've already told you, hysteresis means like this, like circle shape, means we can say like ellipse shape, really like a ellipse shape. Non-linear means just like a saturation like this, like so you can see clearly. Non-linear means you are going to get in this manner, and the hysteresis loop means we are going to get like this. So we are going to get some loop manner. Then what is going to be? We are going to see. See BH loop, BH has a hysteresis loop. Then what is the nature? Again, I mu is going to have a peaky current. Again, we need a peaky value. Then only if current is peak value, then only we are going to get the flux in a sinusoidal fashion. So therefore, again EMF, I already told you EMF is a function of flux only. So therefore, it is also again sinusoidal. And IMU is going to lead flux by some hysteresis angle. So this current IMU is going to lead the flux by small amount of hysteresis angle. So this IMU is going to lead the flux by some amount of hysteresis angle. Suppose I want IMU to be sinusoidal for a BH loop non-linear. Then what is the nature of the flux we are going to get? Suppose if I am going to give a IMU as a sinusoidal current and the BH loop is a non-linear, then what is the nature of the flux? Then we are going to get a flat topped waveform. Then we are going to get a flat topped waveform. So we are going to get a flux of flat topped waveform. And EMF is nothing but it is a differentiation of the flux. So differentiation of flat top waveform is nothing but peaky waveform. These things I have already told you. So EMF is again peaky in nature. So these are the points that you always have to remember. So therefore, let me repeat again. So whenever the BH loop is linear, whenever the BH curve is linear, if flux is sinusoidal, then the current is also sinusoidal in nature, and the EMF is also sinusoidal. Whereas for a non-linear, if the flux is sinusoidal, then we get a huge amount of current. So therefore, we are going to get a peaky waveform, and the EMF is always sinusoidal. Again, if it's having some hysteresis loop means again non-linear. So same thing. For a flux to be sinusoidal, we need a magnetizing current to be peak in nature with the EMF sinusoidal, and IV is going to lead the flux by a small amount of hysteresis angle. Suppose if you want a reverse case, so for the BH to be non-linear, for a BH curve to be non-linear, and I want the magnetizing current to be sinusoidal, then I need a flux to be flat topped waveform, and the EMF is the differentiation of the flux, which is equal to differentiation of flat topped waveform is nothing but peaky waveform. So these are the points that you always have to remember. So under BH non-linear, if the current is sinusoidal, then flux will have third harmonic component as dominant, and if flux is sinusoidal, and then current will have dominant third harmonic component. So listen carefully. Under BH curve as a non-linear, if the current is sinusoidal, then flux will have third harmonic component as dominant. I already told you, for a BH non-linear curve, if the current to be sinusoidal, then the flux will be flat topped waveform. Flat topped waveform is the third harmonic again dominant in nature. And if the flux is sinusoidal, means the current is peak in nature, then the current will have dominant third harmonic component, means we can say that it is going to have a peak in nature. So if one is sinusoidal, the other component will have dominant third harmonic component. So listen carefully. Under BH is non-linear. If one current or flux, if any of it is a sinusoidal, the other one should be always in a dominant third harmonic component. Whether it can be peaky waveform or whether it can be flat top, depending upon the things we have discussed. So the only thing that you always have to remember, whenever a BH curve is a non-linear and the flux has to be sinusoidal, then the IMU should be always peaky waveform. It is going to have the third harmonic as dominant component. Similarly, for the same BH of non-linear, if the current to be sinusoidal, then the flux should be flat top waveform, means it is going to have a third harmonic as a dominant component. So this is the point that you always have to remember. If under BH curve as a non-linear, if one is sinusoidal, the other should have always the third harmonic component as the dominant in nature. So now we will discuss the switching transients in a single phase transformer at no load. So now we are going to discuss the switching transients in single phase transformer at no load. So this is a single phase transformer with the primary winding and the secondary winding. No load means you are not going to keep any load to the secondary side. So as you are not going to keep any load, the current drawn by the secondary side is zero because it's an open circuit. The primary winding is having the turns of N1 and the secondary winding is having the turns of N2. So now here I am going to give a supply voltage of V of t. I am going to assume that I am going to close the switch at a certain amount of time t0. See, whenever I am going to close this switch, then current is going to pass. So if I curl my right hand fingers in the direction of the current, then thumb is going to indicate the direction of the flux in this core. See, even we are not going to keep any load, still a small amount of current is going to drawn by this. From this input, this transformer is going to draw a small amount of current. That is called as the no load current. It is nearly 1% of the full rated current. So now I am going to assume the supply voltage equation is equal to Vm sin omega t. See, as we can say that practically a small amount of resistance and inductance is present, the voltage drop across them is really less. So therefore, the supply voltage is equal to voltage induced is equal to E of t. So E of t is equal to N1 into d phi by dt. So therefore, E of t is equal to N1 into d phi by dt. So what is E of t? E of t is equal to Vm sin omega t is equal to N1 into d phi by dt. So now, E of t is equal to Vm sin omega t is equal to N1 into d phi by dt. So what I am going to do basically, I am going to take dt and n to this one. So finally we are going to get Vm by N1 into sin omega t into dt is equal to d phi. So now I am going to do the integration on the both sides. Integration of d phi is nothing but phi of t is equal to, see, this is the thing that you always have to remember. Vm by N1 is a constant. Integration of sine. Integration of sine is minus cos omega t by, we are going to with respect to t, so therefore omega is a constant, by omega we are going to get. See, plus some constant c we have to write here. So now phi of t is equal to minus Vm by N1 into omega cos omega t plus c. See, but now I am going to assume I am going to close the switch at t is equal to 0. When I am going to close the switch at t is equal to 0, then flux at t0 is equal to 0 is equal to 0, because initially there is no flux in the core. So at t0 is equal to 0, the flux in the core initially at that switching instant is equal to 0. So therefore, what is the supply voltage at t0 is equal to 0? This is equal to 0 because if you substitute in sin omega t is equal to 0, we are going to get 0. So we are going to get 0 is equal to minus Vm by N1 omega plus c. So c is equal to Vm by N1 into omega. So I am going to assume that I am going to switch is closed at the distance t0 is equal to 0. So if you substitute C this one in the above general equation, we are going to get finally phi of t is equal to Vm by N1 omega into 1 minus cos omega t. This is called as the phi max. So phi max into 1 minus cos omega t. Then what is going to happen at t is equal to pi by omega? If you substitute at t is equal to pi by omega, then omega into t is nothing but pi by omega. So omega cancels. Cos pi is nothing but which is minus 1. So minus 2 minus is plus. So 1 plus 1 is 2. So 2 phi max. So therefore we can say that this is called as a doubling effect. Means the flux at t is equal to pi by omega is very high in the core. It is very high. So therefore this is called as a doubling effect. At this instant, large inrush current passes and damages. So because of this doubling effect, we can say that a huge amount of inrush or no load current at the transient state is very high, and it is going to damage the windings also. At this instant, large inrush current passes and it damages the winding of the transformer. So basically what I am trying to say is, if we close the switch at t0 is equal to 0, initially there is no flux in the core. So flux at t0 is equal to 0 is equal to 0. And what is the value of the supply voltage at t0 is equal to 0? It is also 0. So if you substitute the above equation, we got the value of C. And if you substitute the C value, we are going to get this general equation. And if you substitute P is equal to pi by omega, then simply we can say that we are going to get the 2 times of maximum flux. This is called the doubling effect. So because of this doubling effect, a huge amount of inrush current is going to pass through the winding, and the winding is going to get damaged. So we can say because of this doubling effect, we can simply say that the winding, so initially at no load condition, the current in this winding is very very high. So at this instant, large interest current passes and damages the winding at no load condition. So you can see clearly the no load current at omega t is equal to pi. It will be a very very huge, and it is going to damage the winding at no load condition. So this is called the transient state. So this is called as a for transient state. After some time, it is going to have a purely sinusoidal. After some time, it is going to have a purely sinusoidal curve. It is called as in the steady state. Whereas in the transient state, at omega t is equal to pi, because of doubling effect, a huge amount of current is going to pass in the winding, and then it is going to get damaged, which is 20 times the rated current. It is 20 times the rated current. We can say approximately 20 times the rated current. So IR is called as the rated current, and IF is called as the no load current. So this is the characteristics of the no load current. We are going to get initially when you close the switch at T naught is equal to 0, at omega t is equal to pi, because of doubling effects, a huge amount of current is going to pass. It is nearly 20 times the rated current, and the winding is going to get damaged. And what we must do in order to eliminate this huge amount of induced current, or if you remove this doubling effect, then simply we can say we have removed all these crazy things of induced current at huge value. How to remove this one? So I am going to do one small technique. Instead of closing the switch at omega t is equal to 0, I am going to close the switch at t is equal to pi by 2 omega. Instead of closing the switch at t naught is equal to 0, I will try to close the switch at omega t is equal to pi by 2. So at omega t is equal to pi by 2, I am going to close the switch. Then I will see what is going to happen. So at t naught is equal to pi by 2 omega, I am going to see what is the nature of the curve. So omega t naught is equal to pi by 2. So already I have told you initially there is no flux in the core. So flux at t naught is equal to pi by 2 omega is nothing but 0. Then but at supply voltage at t naught is equal to pi by 2 omega, it is nothing but we are going to get a maximum value, because the function of sine 90 is maximum value. So at omega t is equal to pi by 2, we are going to get a maximum supply voltage. So I am going to close the switch at t naught is equal to pi by 2 omega. So if I substitute the general equation, pi of t naught is equal to minus Vm by n1 omega cos omega t naught plus c. So I have already told you at t naught flux is equal to 0, and we can say cos omega into pi by 2 omega may cancels. Cos pi by 2 is nothing but 0. So this is 0 plus c. So c is equal to 0. So finally, if you substitute c is equal to 0 in the general expression, we are going to get pi of t is equal to minus Vm by n1 into omega cos omega naught t is equal to minus pi naught into cos omega t. So now we can see there is nothing like doubling effect. There is no doubling effect. If you close the switch at the maximum value of the supply voltage, if you close the switch at a time when the supply voltage is reaching the maximum value, then there is no doubling effect. If there is no doubling effect, there is no high amount of induced current. So now no doubling effect in flux, so no large induced current is present. So this is the point that you always have to remember. See, flux is directly proportional to current. More is the flux, more is the current. So this is the point that you always have to remember. More is the flux. See, because of current only the flux is producing. Because of current only the flux is producing. If the flux is very high, the magnetizing current is also very high. Here the magnetizing current itself is equal to no load current at the no load condition. So we can say simply that if there is no doubling effect, simply we can say that there is no high amount of induced current. So now we are going to eliminate this doubling effect, or we can say we have completely removed this huge amount of induced current. So now no doubling effect in flux, so no large induced current. So whenever if you close the switch at t naught is equal to 0, yes, there will be a doubling effect. But if you close the switch at the maximum value of the supply voltage, there is no doubling effect. So therefore, there is no high amount of induced current. So now we will discuss harmonics in a three-phase transformer. So what are the types of harmonics that are going to present in a three-phase transformer or in any machine? If you take any machine, what are the harmonics they are going to present? Now we will see what is each and every type we are going to see. Generally for three-phase transformers now we are going to study. So harmonics in a three-phase transformer. See, let me tell you positive phase sequence. Positive phase sequence. Suppose I am going to assume that this is a sequence. So this is IA, this is IB, and this is IC. I am going to assume in this manner. So IB is going to lag IA by 100 degree, and IC is going to lead IA by 100 degree. So each are having the same magnitude, the vectors of equal length, and they are displaced by 120 degrees. So therefore, IA is equal to Im sine omega t, IB is equal to Im sin omega t minus 120. IC is equal to Im sin omega t plus 120 because IB is going to lag IA and IC is going to lead IA. So this is the expression of the currents in a time domain. But if you add all these things, if you add IA plus IB plus IC at each and every instant, it is equal to 0. So if you add all these three components, then we are going to get always equal to 0. We are always going to get a as a 0 value for all the time. So this is A, B and C. So if you go in the clockwise direction, we are going to get A, then B and then C. It means that the phase sequence is A, B and C. So now what is the negative phase sequence? Negative phase sequence is now we have to interchange the way you are proceeding. In the previous case we have gone the clockwise, now go for the anti-clockwise. So therefore it has to be A, B and C. So let me assume for a positive sequence, if you go in the clockwise and then for anti-clockwise you have to, for the negative phase sequence you have to go in the anti-clockwise. Again same A, B and C. So now you can see clearly IB is going to lead IA by 120 whereas IC is going to lag IA by 120. So now if I write the time domain expressions, we are going to get IA is equal to Im sin omega t, IB is equal to Im sin omega t plus 120 and IC is equal to Im sin omega t minus 120. All these vectors of each equal length with a phase difference of with a phase displacement of 120 degrees between them. So if we add all these three vectors, we are going to get 0 always. So IA plus IB plus IC is always equal to 0. So two types of harmonics present in a three-phase transformer they are. So generally two types of harmonics are going to present in a three-phase transformer. So what are they? Now we are going to see. Only two types of harmonics are going to present in a three-phase transformer. They are 3n plus or minus 1 harmonics and also 3n harmonics are also called as the triplet harmonics. So generally there are two types of harmonics are going to present in a three-phase transformer. 3n plus or minus 1 harmonics and the 3n harmonics are also called as the triplet harmonics. So 3n plus or minus 1 harmonics are called as the less dominating. These are the less dominating harmonics. Whereas 3n harmonics or the triplet harmonics are more dominating in nature. So this is the point that you always have to remember. See, there are two types of harmonics are going to present in a three-phase transformer or in general for any machine, which are the 3n plus or minus 1 harmonics. So 3n plus or minus 1 harmonics are always less dominating, whereas 3n harmonics or the triplet harmonics are more dominating in nature. This is a very important point that you always have to remember. So 3n plus or minus 1 harmonics are always less dominating, whereas 3n harmonics or the triplet harmonics are more dominating in nature. So now we will study the 3n plus 1 harmonics. So 3n plus 1 harmonics now we are going to see. Suppose if you substitute n is equal to 1, then what we are going to see here basically 3 plus 1 is equal. See, we are going to consider only the odd harmonics, not the even harmonics. We are going to consider only the odd harmonics in all the cases. See, we are going to consider only the odd harmonics but not the even harmonics. We are going to consider only the odd harmonics. So if you substitute n is equal to 1, we are going to get 4. We are going to neglect it. If you substitute n is equal to 2, we are going to get 7. Yes, we have to consider. And if you substitute n is equal to 3, we are going to 10. So this you don't have to consider. Just you have to remove it. Because I am going to consider only the odd harmonics, not the even harmonics. If you substitute n is equal to 3, we are going to remove that one. Because if you substitute n is equal to 4, we are going to get 13. So we have to consider only the odd harmonics, not the even harmonics. So now see, listen carefully. Now I am going to consider the seventh harmonic. What is the nature I am going to see? See, for the positive sequence, I am going to see what is the nature. So IA7 is equal to Im sin 7 omega t and IB7 is equal to Im sin 7 omega t minus 7 into 120 is nothing but 840. So see, basically what I am trying to say simply, just assume a phase sequence of A, B, C in the clockwise direction, A, B and C. Then I will see what is the nature. IA is equal to, already I told you, IA is equal to Im sin omega t, IB is equal to Im sin omega t minus 120 and IC is equal to Im sin omega t plus 120. So IA7 means just in place of omega write 7 omega. So Im sin 7 omega t, whereas IB7 is equal to Im sin 7 times of omega t minus 120. It means 7 omega t minus 7 into 120 is nothing but 840 is equal to, if you do the simplification, we are going to get finally Im sin 7 omega t minus 120. So same thing we are going to get here. So this is the same thing we are going to get. IB7 is going to lag the IA7 by 120. Similarly, IC7 is equal to Im sin 7 times of omega t plus 120. 7 omega t plus 120 into 7 is nothing but 840. With this simplification, we are going to get Im sin 7 omega t plus 120. So you are going to get same thing, same phase we are going to get. IC7 is going to be the Ia7 by 120. So you can see clearly, again same thing is going to get happen. So the phase sequence is not changed. Whatever the phase sequence of ABC, same phase sequence we are going to get again. So it is called as the, suppose whatever the phase sequence of the original vectors ABC, same phase sequence is present. So therefore we can say this is to be positive phase sequence. So if we add all these vectors, IS1 plus IB7 plus IC7, at every instant it is always equal to 0. So therefore 3n plus 1 harmonics are all have the positive phase sequence. Means whatever the original vector phase sequence, same phase sequence will be present for even positive phase sequence also. So always 3n plus 1 odd harmonics. So 3n plus 1 odd harmonics will always have 3n plus 1, all the odd harmonics will always have the positive phase sequence. Means they are going to follow the same principle of the original vector's phases. So now we will see what is the nature of the 3n minus 1 harmonics. So 3n minus 1 harmonics, substitute here n is equal to 1, we don't have to take the, you can just take the odd values. So if we substitute n is equal to 2, we are going to get 5. So like that, you have to substitute n is equal to 1, 2 and goes on. Only take the odd harmonics, not the even harmonics. So I am going to consider this 8th one also. Just to consider the odd harmonics only. Then I have already told you I am going to assume the original phase sequence of ABC in the clockwise A, B and C. I have already told you Ia is equal to Im sin omega t, Ib is equal to Im sin omega t minus 120 and Ic is equal to Im sin omega t plus 120. So now you will see what is the nature of the fifth harmonic. So if you substitute here Ia5 is equal to Im sin phi omega t. So this is the phase sequence of Ia5 and Ib5 is nothing but Im sin of 5 times of omega t minus 120. So take 5 inside, 5 omega t minus 5 into 120 is nothing but 600. So with simplification we are going to get Im sin 5 omega t plus 120 means now it is leading the Ia5. So Ib5 is going to lead the Ia5. Similarly Ic5 is equal to Im sin of 5 times of omega t plus 120. So if you take 5 inside we are going to get 5 omega t plus 600. So finally we are going to get Im sin 5 omega t minus 120. So this Ic5 is going to lag Ia5 by 120 degree. So Ic5 is going to lag Ia5 by 120. So now you can see clearly the phase sequence is changed. So if you go in the anti-clockwise, you are going to get ABC. So this is opposite to the original phase sequence of the vectors. So we can see it is said to be a negative phase sequence. So if we add all these vectors, Ia5 plus Ib5 plus Ic5 is always equal to 0. So if you take any equal vectors, if you take any equal length vectors, if they are displaced by 120, then all the summation is always equal to 0. So remember this point. Whenever if you take any three vectors of equal length and if they are displaced by 120, then the summation will be always equal to 0. So we can say that 3n minus 1 harmonics are all having negative phase sequence. So 3n plus 1 harmonics, all the odd harmonics are 3n plus 1, all the odd harmonics are always are going to have the positive phase sequence, whereas the 3n minus 1, all the odd harmonics are going to have the negative phase sequence. So positive means plus 1 means positive sequence, minus 1 means negative phase sequence. So positive phase sequence means these vectors will have the same phase sequence of the original vectors, whereas the negative phase sequence means these vectors will have the phase sequence opposite to the original phase sequence of the vectors. So this is the point that you always have to remember. What is the nature of the 3n harmonics? So 3n harmonics is nothing but if you take 3n, if you take the 3 inside, then we are going to get, see, Im sin 3 omega t, Im sin of 3 omega t minus 3 into 120, again Im sin 3 omega t plus 3 into 120. All these things are going to have in a same phasor. So Ia3, Ib5, Ib3, Ic3 all will be in the same horizontal direction, means they are all in the same phase. So therefore we can say these are called as the zero phase sequence vectors because they are all always in the same direction. So finally I can say that 3n plus 1, all the odd harmonics are the positive phase sequence, whereas the 3n minus 1, all the odd harmonics are the negative phase sequence, whereas the 3n harmonics are the zero phase sequence vectors. So this is the point that you always have to remember. And the 3n harmonics are always dominating in nature, whereas 3n plus or minus 1 harmonics are always less dominating in nature. So let me take a star connection and a delta connection and let me see what is going to happen. Suppose I am going to assume a star connection. The line currents are Ia, Ib and Ic. So if you apply the KCL at this point, then IA plus IB plus IC is always equal to 0. So therefore, here if you take the delta connection and if the line currents are IA plus IB plus IC, if you apply the KCL at this super node, super junction, IA plus IB plus IC is equal to 0. So you can see clearly IA plus IB plus IC is always equal to 0. Whereas in the 3n harmonics, all the vectors are in the same phase sequence. So definitely their summation will be not equal to 0. So this is the point that you always have to remember. See, the summation of the vectors in the positive sequence and the negative sequence will be always equal to 0. Whereas for a zero sequence currents, the summation will be never equal to 0. So it means that 3n plus 1 harmonics and 3n minus 1 harmonics will definitely have all the summation of the vectors will be always equal to 0. Whereas for a 3n harmonics, all the lying in the same phase, so their summation will be never be equal to 0. That is the thing I am going to translate this case. So IA plus IB plus IC is always equal to 0 for star connection and also this delta connection. We can see that 3n plus or minus 1 harmonics present in line currents of both the star connection and the delta connection. So we can say that as IA plus IB plus IC is equal to 0 for the star connection delta connection. So we can say that 3n plus or minus 1 harmonics are going to present in the line currents of both the star connection and the delta connection. So always we can say as the IA plus IB plus IC is equal to 0 for the star connection and also the delta connection. So always 3n plus or minus 1 harmonics are going to present in the line currents of both the star connection and the delta connection. Whereas the 3n harmonics will never present. 3n harmonics will never present in the line currents of in the line currents of both the star connection and also the delta connection. So listen again. 3n plus or minus 1 harmonics are going to present in the line currents of both star connection and the delta connection, but 3n harmonics will never present in the line currents of star connection and the delta connection. So now we will consider the 3n harmonics. Then we will see what is the nature. As I have already told you, IA is equal to Im sin omega t, IB is equal to Im sin omega t minus 120, IC is equal to Im sin omega t plus 120. Then we will see the third harmonics. Let me assume a third harmonic of 3, and we will see what is the nature. IA3 is equal to Im sin 3 omega t, IB3 is equal to Im sin 3 omega t minus 3 into 120, which is 360. So if we solve this one, we are going to get Im sin 3 omega t plus IC3 is equal to Im sin 3 omega t plus 3 into 120 is again 360. So if we solve this one, we are going to get again Im3 sin 3 omega t. If we add all these vectors, it will be never be equal to 0 because all these are going to lie in the same phase sequence, which is called as these are basically 0 vectors. The summation will be never be equal to 0. So this is the point that I am trying to say. So in the star connection and delta connection, only the 3n plus or minus 1 harmonics are going to present, but not the 3n harmonics. So here, take a star connection load here. As I have already told you, if I apply the KCL at this junction, IA plus IB plus IC is equal to 0. But see, I have already told you IA plus IB plus IC is equal to 0 means these line currents can have 3n plus or minus 1 harmonics, but not the 3n harmonics. 3n harmonics will never absent, will always absent in this case. So 3n harmonics will always absent in this case. Only 3n plus or minus 1 harmonics are going to possible in this case. So IAB3 plus IB3 plus IC3 will never be equal to 0. So 3n harmonics are not present in a star connection without grounding in line currents. Suppose if there is no grounding, then definitely we can say that only 3n plus or minus 1 harmonics are going to present in the line currents, but 3n harmonics currents are never going to present in the star connection without any ground. Suppose if the ground is there, then what is going to happen? So this is the line currents IA, IB and IC. This is the neutral current IN. If you apply the KCL, then we can say IA plus IB plus IC is equal to IN. IN is not equal to 0. Then we can say that then it is not equal to 0 means 3n plus or minus 1 harmonics will never present now in the line currents. Only the 3n harmonics currents are going to present. So simply we can say that IA3 plus IB3 plus IC3 is equal to 3Im sin 3 omega t is not equal to 0. So 3n harmonics are present in the star connection without grounding, with grounding in line currents. So in this case, only 3n plus or minus 1 harmonics are going to present in the line current, but never 3n harmonics. But in this case, 3n plus or minus 1 harmonics will never present in the line currents, but only 3n harmonics are going to present in the line current. So this is a point that you always have to remember. So 3n plus or minus 1 harmonics will always present in this case without grounding, but the 3n harmonics will never present here. Whereas here 3n plus or minus 1 harmonics will never present in this case, but only 3n harmonics are going to present in this case. So if there is a grounding, so listen, if there is no grounding means simply we can say that for a star connection, if there is no grounding means 3n plus or minus 1 harmonics are going to present, but not the 3n. If the grounding is present means 3n plus or minus 1 harmonics will never present, but only 3n harmonics are going to present in the line currents. Suppose now if it is a delta connection, then what is the nature? I already told you in delta connection, if you apply the KCL at this super junction, IA plus IB plus IC is equal to 0 always. So whenever IA plus IB plus IC is equal to 0, then I have already told you 3n plus or minus 1 harmonics are going to present in the line currents, but not the 3n harmonics are not going to present in the line currents. Whereas the phase currents, now you see the phase currents, this is IAB, IBC and ICA. So IAB is equal to IBC is equal to ICA is equal to Im sin 3 omega t. So IAB plus IBC plus ICA is not equal to 0. So IAB is equal to IBC is equal to ICA is equal to Im sin 3 omega t. If you add all these things, it will never be equal to 0. So we can say that the phase currents are now going to have only the 3n harmonics, but not the 3n plus or minus 1 harmonics. So phase current contains only 3n harmonics, and the line current won't contain 3n harmonics. So listen carefully. Phase currents will contain only the 3n harmonics, and the line current will contain only the 3n plus or minus 1 harmonics. This is what I am trying to say. So listen carefully. In a delta connection, for a phase currents only 3n harmonics are going to present, whereas the line currents only 3n plus or minus 1 harmonics are going to present. This is what I am trying to say from the starting onwards. 3n harmonics current requires one of the two things to present. See, if 3n harmonic currents are going to present, then these things should be always there. Then only 3n harmonics are going to present. So 3n harmonics current requires one of the two things to present. So in these two, at least one is there means definitely the 3n harmonics are going to present. Either there will be a path to ground, or there must be a closed path. There should be any closed path, or there should be a path to the ground. If anyone is there means definitely the 3n harmonics are going to present. So whenever there is a ground, a path to ground or a closed loop, definitely we can say that 3n harmonics are going to present. So 3n harmonics current requires any one of the two things to present, which is either there will be a path to ground or there must be a closed path. See, if there is a path to ground means definitely 3n harmonics are going to present, or if there is any closed loop means definitely 3n harmonics are going to present. So this is a blind rule you have to think. So whenever is there any path to ground, then definitely 3n harmonics are going to present. If there is any closed loop, then also 3n harmonics are going to present. Let me see a small case of 3-limb code. So this is the limb 1, limb 2 and limb 3. So winding 1, winding 2 and winding 3. So this winding is going to produce a current of, produce a flux of 5A, and this winding is going to produce a flux of 5B, and this winding is going to produce a flux of 5C. So if you apply the KCL, if you apply the you can say flux law at this junction, you can say 5A plus 5B plus 5C is equal to 0. So 5A plus 5B plus 5C is equal to 0. So this 3-limb core will have less insulation. It has less insulation, and it is used for the high voltage with a low kVA rating. It needs very less insulation, and also it is used for the high voltage and the low kVA rating, and less mechanical support is also there. And if you see clearly, 5A plus 5B plus 5C is equal to 0. So 3n harmonic component in flux is absent, but 3n harmonic components in winding currents exist independent of the connection type. So I have already told you 5A plus 5B plus 5C is equal to 0. It means that there will be no 3n harmonics. There will be only 3n plus or minus 1 harmonics are going to present in the flux, but not the 3n harmonics. So only 3n plus or minus 1 harmonics are going to present in the flux, but not the 3n harmonics. So 3n harmonics components in the flux is absent, but 3n harmonic components in winding currents exist independent of the connection type. If in flux, if there is no 3n, means definitely in the windings, yes, 3n harmonics are going to present. So this is the thing that we always have to remember. If in the flux there is no 3n harmonic, means definitely in the current, definitely there will be a 3n harmonic, vice versa. So if in one it is not there means in other it will be always there. So here in this case in the flux there is no 3n harmonic. So definitely in the winding, irrespective of the connection, definitely 3n harmonics are going to present. So 3n harmonic components in flux is absent, but 3n harmonic components in winding currents exist independent of the connection type. So now let us take another example of 5-limb core. So limb 1, limb 2, limb 3, limb 4, limb 5. So now you can see clearly this is going to generate a flux of 5A, 5B and 5C. So now this is a 5-limb shell type. So more insulation is required because more number of cores are there, and it is used for the low voltage and high kVA rating, and more mechanical support is also present because we have extra 2 limbs, so more mechanical support. So now you can see clearly here there is a closed loop is definitely possible. So because of closed path, 3n harmonic components, see whenever there is a closed path for the flux, definitely we can say simply that whenever there is a closed path for the flux, definitely we can say 3n harmonics are going to present in the flux. Then irrespective of the connection of the windings, there will be no 3n harmonic components in the currents. Because of closed path, 3n harmonic components present in the flux, so no 3n harmonic components in the winding current independent of the connection type. So as you can see clearly there is a closed path. Whenever there is a closed path means there will be a 3n harmonics are going to present in the flux. Then definitely if in flux it is there means in current it will be not there. So irrespective of the type of the connection we prefer for this 5-limb core, the 3n harmonics will never present in the winding currents, irrespective of the type of connection you choose. So 3n plus or minus 1 harmonics can flow in both star and delta. These are not dominating and the total current is approximately seems to be sinusoidal. So 3n plus or minus 1 harmonics can flow in both star and also delta. These are not dominating and the total current is approximately seems to be sinusoidal. I have already told you 3n plus or minus 1 harmonic currents are less dominating in nature, and this can flow both in a star connection and also the delta connection. So this can flow in both the star connection and also the delta connection, and these are less dominating. So therefore the current will be always purely sinusoidal. So 3n plus or minus 1 harmonics can flow in both star and delta. These are not dominating and the total current is approximately same to sinusoidal. Because these are less dominating, the current waveform is not altered by these components. We will see some more about this 3n harmonics. See connection and the 3n harmonic current and the 3n harmonic flux. What is the things now we are going to see? See connection with the star connection. So if the star connection means there is no ground. So if there is no ground means simply we can say that it is absent in the 3n harmonic current. So it is absent in the 3n harmonic current. I have already told you star connection means IA plus IA plus IC is equal to 0. IA plus IA plus IC is equal to 0 means we can say 3n plus or minus 1 harmonics are going to present in the line currents of the star connection, but no 3n harmonics. 3n harmonics are absent in the current. If in the current it is absent means in the flux it will be present. So present only in the 5-limb shell type. So present only in the 5-limb shell type. Okay, we start with ground. So whenever start with ground means I want to told you IA plus IB plus IC is equal to IN, then definitely no 3n plus or minus 1 harmonic components in the line currents. Only 3n harmonics are going to present in the line currents. So only 3n components of the current are going to present in this line currents, and these are peak in nature. If in line current it is present means in the flux it won't be present, means it is absent in the flux. Similarly for delta connection, I have already told you in the delta connection the line currents will have only the 3n plus or minus 1 harmonics, whereas in the phase currents, yes, only 3n harmonics are going to present. So in the phase currents only 3n harmonics are going to present, as it is present, whereas in the line currents only 3n plus or minus 1 harmonics are present but not the 3n harmonics. So 3n harmonics are absent in the line currents and is present only in the phase currents. Phase currents are responsible for production of the flux. So phase currents are responsible for the production of the current. So production of the flux. In current if it is present means in the flux it will be absent. So therefore this is the point that you always have to remember. Because of phase currents only flux is produced. So therefore if it is present in phase currents means it should be absent in the flux. So 3n harmonics are absent in the flux.